Hello, you all. Darrell Berry Jr. here, back with some more physics. I'll be doing some moment of inertia problems that I find online. First, I want to go back to the problem that we were looking at the other day for a better understanding of what was going on. It'll be a good warm up as well. So we had a problem like this. So this is my x, y, and z axis with the right hand rule. And we had a particle that was situated here. So why don't we say here? So what was going on is that the particle is out this way and out this way. And I'll make it a little bit more complicated so we can have an idea what it looks like, what is more realistic. Let's say that the mass is a mass m. And I have my references and such in the corner. Did I pick the right video? Wait a minute, I didn't pick the right video. It's close by the when I'm putting references in the chat in the description as we go along. I think I picked the wrong video. Hold on. The people I'm looking at is Michael Beinzen. Really cool. Like he's doing everything symbolically first, which I suppose is cool. It's a good habit to get into. I'm going to make my numbers slightly different just to see what it looks like. Matter of fact, why don't we make this even more challenging just to see what we're looking at? Only thing about this, I don't have the solution to the thing, but what we do. So see the best way to draw this. So if I draw this vertical line here, duplicate it, here, duplicate it here, so just duplicate that. So what I have here is a particle that is not necessarily in the XY plane anymore, or not at all in the XY plane. See if I can get this one worked out. So let's say that I should get an idea of what the sizes are. Let's say the particle is at 2, 3, that seems reasonable for that. And these are in meters. Meters. And let's say that it's a particle with mass of 2 kilograms. Particle. Did I go the radius? Does the radius matter? they are meter. So that means we can get a density out of this. So particle density is going to be mass over volume. Is going to be so why don't we get some particle volume equations? It must be some kind of thing with a whole bunch of volume stuff, okay? So a sphere or volume area. So a sphere is 4/3 and surface area is 4 pi r squared. Um, right circular cylinder. Right circular cylinder. Okay, yeah, cylinder. So sphere, cone, pi, h, h, um, surface area, right circular, cone, r, scrap, pi, r plus square root of h plus h squared plus r squared. All right, that need to make more space. Right, so we have right circular plane, r plus root of I mean, those are the main ones. For cone, would be nice if I had a pyramid, but I guess that's easy enough to figure out. I think maybe volume of a pyramid. So I'll just figure that out. Don't worry about that. No, it's not. So we have the density is m over v, which is m over 4/3 r cubed, which is 2 over. We have to drop out unexpectedly, but if I do, I'll be back. So this is sort of an impromptu session. Something may come up. 4.2 meters cubed equals about 0.48 kilograms per meters cubed. And I'm not sure how we'll leave that there. So we want to get the moment of inertia of the particle at that point. I wonder, let's look at the formula first. Let me remind myself of what it is. Awesome. Thank you, Aaron. I appreciate it. So the formula should be I equals, we'll say Ij, and I'll make this in blue, equals uh, the integral of the mass times r squared, whatever that is, the chronometer delta, Ij, minus xi, xj, and since we have a distribution of mass, we need to make that into a volume integral. So it'll be integral dv uh, r squared Hanukkah delta minus xi xj rho. Let me know if you have any questions, Aaron. I am checking the chat regularly. So it should be this. Let me pull up my formula previous. I'll be looking at some notes as I go to try to help make sure that I give you the proper answers and solutions and all of that good stuff. So don't mind me if I pull up a few things. And this seems good. Iij, integral volume. This will be the volume as it relates to the radius vector, r squared. Right. Let's see what we have here. So the center of mass, the good thing about that is we know the center of mass is in the center at the absolute center of the sphere. So that's good. So the center of mass would be at the 2, 3, 1 coordinate. So we have a sphere. So what it is, we don't have to actually use spherical coordinates, I don't think. I think we're pretty sure we can treat this as a point still. Because the radius is working through so spherical coordinates. We have x equals r for rho, for the mass with our sphere, rho cosine. I'll do physics coordinates because I guess I'm used to doing the math coordinates. So basically with if I was to draw this on the side, we have theta coming down. We have phi going over, and then we have rho, which is the length. So if you see what I'm doing here, the vector is coming out this way. So this is a vector in space. This is the x, y, and z axes. And this dotted line right here is the vector projected onto the xy plane. So the vector is out in the air like that. Hey, what's going on, Rabbit Riker? Good to see you. Let me know if you have any questions. So if I was to do this well, even that shouldn't matter. The particle is a sphere, but it's positioned just floating in the air. Okay. So that's one of the things I'm learning is not to make these problems more complicated than they need to be. Right. So what we're going to do is we're going to model this thing. I mean, that's good to know. What we're going to do is we're going to model this object as a point particle because all of the mass is centered here. So the moment of inertia should behave as if it's a point particle with mass 2 kilograms. So we'll try that. So that means that the radius is just what that is right there. And we know that r, let me go back to that. We have r squared equals x squared plus y squared plus z squared. So we're going to plug that in for r. And the Kronecker delta is going to be 1 if the values for the parameter we want. So let me make sure I'm clear about what we're doing. You want to have a moment of inertia tensor, which is going to be ixx, ixy, ixz, iyx, iyy, iyz, and izx, izy, izz. So this is going to allow us to understand the moment of inertia for this sphere that we're modeling as a particle that's floating out in 3D space there. It's going to allow us to model this shape as a point and find out how hard it is to move it. So basically the moment of inertia is basically the equivalent of mass in a rotational space. So just like how if I'm a rocket going through space, the propellant has to move that rocket. So you have F equals ma. So mass, you can say, relates to how much acceleration is going to experience versus how much force. We have, what was the equivalent? So I equals m r squared, but L equals I omega. Or is it torque equals I omega? I mix up which one. Yeah, it's torque. So in this case, the phi is the angular acceleration, or at least the omega. The omega is the angular acceleration. The I is the moment of inertia, which takes the place of mass. So it's going to be how massive the particle is and how far it is away from the axis of rotation. And then you have torque. Let me look that up to make sure I wrote that properly. We actually can have a formula sheet, but I guess I get in the habit of trying to memorize everything. Maybe I need to stop doing that so much, especially in graduate school. Torque equals I A. I'm going to use a different symbol there. I'll look up torque, the moment of inertia, and confirm that's so they're doing angular, yeah, they're doing angular acceleration, right? So this should be angular acceleration. That's the difference. So it did look kind of strange for a reason. All right, so there we go. Okay, that makes sense. Because you have F equals ma, that's acceleration. So whereas torque equals ia. All right, so there we go. So those are the equivalents of the formula. So it's like moment of inertia is the equivalent of mass as far as a circular movement. So what we're doing right now is we're finding the I, and this amazingly, this process gives us the moment of inertia. This is the moment of inertia here in every single possible angle around which we can move this particle. So I can take and move this particle in the x direction. So if you see that this is the x-axis here, and the vector for angular velocity or angular acceleration, it goes so that your thumb is along the axis. So if I put my thumb along the x-axis, if you look at the page, I guess it's reversed for you all. So my thumb is going along the x-axis, so the rotation is going to be that way around the x-axis. If I also face it your way, so in your direction, it's coming out the page. So the rotation is that way. So that means that the rotation will be this way for a positive omega here in the x-axis, right? So and let me, yeah. So that means that if I wanted the particle to go in that direction, I will have to push it up this way. So this direction, and maybe I should make this a different color here. So this would be torque in the x direction, because if I push up in that direction, it'll cause the particle to go like this, and thus it's rotating in a direction that matches the angle omega x that I put on the particle. And Rabbit says, yeah, I can't see I wet the bed again, Mom. So let me pull the video up online. Maybe it's something to do with my connection or something. Let me see. You need to disconnect the chat and reconnect. Oh, I see you now. No, I don't see. I'm sorry. I see the comment mentions them. Just try again. Try to type again. And there could be some issue going on with the chat. I am on Discord as well. That could be what it is. Yeah. Thank you. There we go. I apologize. I didn't realize I had to click the all messages there, the live chat. Let me make sure I go through all the comments. Answering the content as always. Thank you, Aaron. Wet says hello. Hello to you as well. Good to meet you. I have a cosmology question, but I'm happy to wait till the end. Sounds good. Let me finish this problem, and then we'll take a break and do some cosmology. Rabbit says hi there. Wet says I have a question. Awesome. I can see you now, Wet the bed. Let me know what your question is. Thanks for the tip on the messages, Rabbit. I'll need to make sure to click click that button. And I know again is writing the question, so I'll wait for that. So the same thing. If I were to do the torque in the x direction, this would be torque x. Excuse me, or z direction I meant to say. Because if I push the particle that way, you see how it's going around the z-axis counterclockwise. It's going to push the particle this way. Therefore, it matches the vector for the right-hand rule for the z-axis. By the same token, if I push the particle down this way from where it's at, and we're imagining that if I push the particle down that way, it's tethered to the y-axis, and then it'll go around the y-axis like that. So to clean this up a little bit, so it's a bit more clear, we can see that those are the directions of the torque that we could apply to the particle to get it to go around the relevant axes. And this, what we're doing right now, will give us the values of the moment of inertia in each of these directions. There we go. So we have the x going up, the y going down, and the z going straight forward across the page in the xy plane. All right, so let's go ahead and do this thing. And again, I'm modeling, since it's a sphere, relatively small sphere, I'm modeling this as a point with mass 2 kilograms, and we'll see if that works. And actually, you know what I'll do? I'll still actually utilize the density, even though I'm doing the positioning as if it's a point. All right, let's do this. So we have Ixx equals integral. Oh yeah, okay, I see what's going on. So the volume is the volume of the Withrow column at the place that it's at. Now what I can do is, we have a value for rho, 0.5 kilograms per meter squared. We have the volume. Okay. So we're going to see how this plays out. I never did this problem. We're going to work it out and see what happens. Rho, volume, and then we have r squared. That's going to be x squared plus y squared plus z squared. And since it's Ixx, the Kronecker delta, so the Kronecker delta there, when you see something like this, what this means that, let me draw it a bit clearer. This means that if I equals j, it equals 1. And if I equals not j, it equals 0. So this is going to come into play later. It's very important to keep in mind what this Kronecker delta thing means. So right now we have x and x, so those are equal. So that's going to equal 1. And this is going to be minus xij. Both of those are xx. So this is minus x squared. Then we have dv. And so we're going to have integral, and x is from, actually I'll just do the integral first and I'll add the bounds later. So let me, I add the bounds as we go. Rho, x squared plus y squared plus z squared minus x squared, that's y squared plus z squared. And we have dx, dy, dz. So this is what we have. So this is going to end up being slightly complicated since I have a 3-dimensional integral. So why don't we do the x first? So we have x is going from 0 to 2. Maybe I should put that here. And I'm doing a little bit of rounding since I'm modeling it as a point. Suppose if it was a bigger sphere and make a bigger issue. I may have to do one later as a bigger sphere. 0 to 2. I will do a harder problem later. It does say marathon, so but this is like a warm-up. 0 to 2. Then we still have y squared plus z squared dy dz. That's going to clearly be 2 row uh, integral uh, y squared plus z squared dy dz. So why don't we go y next? So this will equal 2 row y3 divided by 3, and y is from y is from 0 to 3, and then we have plus z squared, and y is from 0 to 3 dz. So just integrated y. So this would be 2 row uh, crap, 27 divided by 3 plus 3z squared dz, and still have the z integral. Let me know if you see me making a mistake. I think Daryl is open to your question now. Oh yeah, let me know if you have a question about this problem here, and I'll happily answer it. And as soon as I finish this problem, what I'll do is get through the moment of inertia tensor. So I have these 9, and then I'll answer the cosmology question. And there's some symmetry here, so shouldn't be exceptionally long. All right, so we have this. Let me check and make sure I didn't make an error. Boom, rho times all of that. Y squared, x is multiplied by both of those. Is going to distribute, so that's fine. So basically we could treat this like that. So the x is still being multiplied by everything. We still have the z integral here, and rho is still multiplied by everything. We have that. That seems right. And we take the y by itself, the y with the z. Hold up. Draw this better. I made my 7 look a little bit like a z. 27. And that was y by itself, so I didn't have any z. And 3 there. All right, so I think we're good. So then we have 2 row integral. This 3, that's what, 9 z. And z is from 0 to 1, thankfully. And then we have 3z cubed divided by 3, 0 to 1. I actually going to pick some all right numbers this time. So we have that equals 2 row. And then we have 9 minus 1. So they equals 2 row times 8. So they equals 16 row. So it seems like there should be more details, but I am modeling this as a point. So we'll get to a more complicated problem later. All right. So one thing I'm missing is the units. I think I dropped my unit. So this is a integral of this is a volume integral. So we have each of these inputs are meters. So what we would have is should be meters cubed. Let me just make sure. Should it be meters? No, I'm integrating, so let's see. Meters, integrate. So this would be 2 meters. Dun, dun, 2, 2, be meters. So it will be meters. Meters cubed. Cubed. So this will be meters. This would be meters to the fourth. I'm looking at that correctly. And meters to the fourth. So this is meters to the fourth and meters. So if I'm looking at this correctly, this would be meters to the fifth, right? So when I plug this in, we have 16 times row ones. I would just make it 0.5 kilograms over meters cubed times meters to the fifth. So we have, oh crap, I think I left my radius off. No, it is it. FMR squared. Oh, kilograms. Yeah, seems like the units are working out. So then I have what? 8 kilograms times meters squared. And that is what we need. That equals I. So we look at this, we have the M, the mass is kilograms, and the R squared is meters squared. So we do have kilograms per meter squared. So that seems right. I'll take a moment to see if anybody have any questions so far. Have you been paying attention to the 3L Atlas, and what do you think? I have not actually. I've been knee deep in graduate level physics and astrophysics. Not so much the um, current research going on in general. I can take a look real fast. All right. So interstellar comet. I'll share this and we'll take a look at it. So I have a page that I found on NASA. So of course I do like comets. What is the best way to change my share? I should have a window for this already. Maybe I don't. All right, so let me just add one. All right. I'll put window capture. And this window here. All right, let's take a look. And let me clean up the window a bit. Didn't mean to change that one. I'll zoom this down some. That seems sufficient. And the bottom seems sufficient. All right, so that seems good. I'll just make that an even value. Ah, well, some people think. I remember we had that Oumuamua, and one of the physicists thought it was a extraterrestrial object. Is it something like that where people think it's different things? People think it might be an extraterrestrial object. Put this where I can find it easily next time. By the way, boom. All right, there we go. So we have Comet 3L Atlas. NASA missions are working together to track and study this rare interstellar comet as it passes through our solar system. Okay, so they're already highlighting that it's from outside the solar system. And even looking at the trajectory there, if you look at this image here, you can sort of tell it's from outside the solar system by the trajectory it has, and also the speed, the velocity it has as well. So, what opinions do they have on it? Hopefully, this plays again. There we go. All right, that's neat. Would it be visible? No, seems like it should be visible. It's on the night side of the Earth. It's moving past the sun. So just like how we can see Venus on that side, it seems like it should be visible. Even though I don't know if you may need a telescope. That's because of its motion, position in the Milky Way, its acceleration away from the sun, and the lack of tail visibility. For the tail visibility, what? I mean, other than being far away, too far away from the sun for the solar wind to make a real difference, what would the lack of tail visibility say? Again, trajectory. All right, let's look at a little bit of what this has. A NASA-funded Atlas asteroid terrestrial impact last alert system. Now, my understanding is they made systems like this uh, when the Oumuamua came through, so they could be ready for stuff that comes through. Survey telescope in early first report observations of the minor planet center of Comet 31 Atlas in July 1st, 2025. Since first report, observations may be for discovery were gathered from the archives of 3 different Atlas telescopes around the world. Comet's a general name for the discoverers, in this case, the Atlas survey team, I for interstellar. Okay. Yeah, I guess you do need some pretty serious telescopes to see it. There it is there. You can see it moving against a starry background. And that is pretty small. I mean, you can see how deep the image is because there's so many pixels in the back that are lighted. So it seems like a pretty deep view. Animation showed the observation of 3L Atlas when it was discovered July 1st, 2025. The NASA-funded Atlas survey telescope in Chile first reported the comet. All right. Was first discovered 277 million miles from Earth. I mean, looking at all the top of my head, looking at this, I would say with the average telescope, no, because of how zoomed in it is. Especially if we don't have any tail visibility, because usually the way we see a comet is the matter that's being ejected from the comet due to the pressure from the sun, the radiation from the sun. So, being that it doesn't have any lights, probably be very hard to see with a telescope. You'd have to have a highly zoomed telescope because you could tell by how zoomed in this is, at least based upon my experience. Like, the more zoomed in you are, the more stars you're going to see in the background, and it's like littered with stars, and the stars are a lot bigger than the object. So, but I could be wrong about that. I have experience with a certain type of telescope, a Dobsonian telescope. It's only 3.5 miles big. So, for instance, so think about it this way. When I look through my telescope, it's a what? An 8-inch Dobsonian, and we had a viewing day out here outside of my university, an unofficial viewing day a few months ago, I guess. And so if we look at the where this thing is passing through, it's passing inside the orbit of Jupiter. That's still pretty close. So let's look at Mars. When I looked at Mars through my telescope, Mars looked like a little bitty dot. I mean, it was enough where I can see the ice caps. So I sort of Mars was tilted in such a way where I could see the ice caps. I could make out that there was ice at the top. But still, it was small. Like, I couldn't like see any details on a planet or anything. I just, other than the fact that, okay, there's one side of it that I could tell is whitish. There must be, snow on the poles. I meant to say, on the poles. And Mars is what, half the size of the Earth, something like that, 3/4 the size of the Earth. This thing is beyond or just at the range of Mars and is only 3.5 miles in diameter. So this thing is a very, very small fraction of the size of Mars, and Mars looks small. So that's why I say that it's very unlikely to be able to see this thing, being that it doesn't have a tail. So these people who found this thing, they're using a very large, you know, telescope designed for this asteroid terrestrial impact last alert system. So it is literally designed to look for asteroids so that we don't get hit by something unexpectedly. So I doubt that we'll be able to see this with a regular telescope. But again, that's just with my experience with my telescope. Okay, this is by Hubble. Hubble takes some deep images, and it's still small and blurry compared with the Hubble. Well, but that's when it was 277 miles from Earth. Right? But I guess we'll still see more as time evolves.
Turning their attention to an unusual object speeding through our solar system. NASA-funded telescopes have their eyes on the sky all the time. And first, NASA space telescopes like Hubble.
Hold up, they showed the telescope. Hold up. Here it is. Look at that.
To ground-based studies, NASA space telescopes even more.
Yeah, so they use some serious telescopes to look at this thing.
And spacecraft in orbit and on the surface will try to catch a glimpse.
Nice.
After that, it's on toward Jupiter.
So the telescopes on Mars are going to try to take a look. So, I mean, it looks like we will be able to get some images. Awesome. Thanks for bringing it up. It seems interesting. So now I'm sure I will keep an eye on it to some extent. Y'all can let me know what you think the scientists think it is. I'll bookmark that. Oh, and let me put this link in the page, by the way, as one of the references that we did. Let me put that in the chat if y'all want to know what link that was. And I shall also put it in the description of this video in my little references section. All right, so we have that. Hey, what's going on at Astra? Doing some moment of inertia tensor stuff, some grad level physics stuff where you basically solving 9 problems at once. That's what they're doing. That's what they're doing. Solving 9 problems at once. All right. Let's keep on going. So we have IXX. I'm tempted to copy this whole thing and just change a few things, but I'm very likely to make a mistake if I did that. Very likely to make a mistake if I did that. But let me just think about it for a moment. Let me see what I would have to change. Yeah. But yeah, I think that might be a bad idea. Let me just do the whole thing again. Except for the first part. I copy this to the equation. So I'll just copy this. All right. So we're going to get I'm going to get all the diagonals first. All right. So to highlight what we're doing here, I just got the IXX moment of inertia tensor. So I just got this one. And I'm going to go down the diagonal first and get those. So we have IYY. And so that means that this will be y, because again, we're just using this equation here, ij, and both I and j are y at this point. So they're the same. So we keep our Kronecker delta, which is going to be 1 when they're the same. And there we go. So now we could just do this integral here. And it should be I mean, really, it should be the same integral as the last one. Let's take a look at this. No, it won't, because the bounds are different. Okay, yes, I'm gonna have to do this. So we have integral rho, and y is in the mix to be subtracted now. Then I'm going to have integral x squared plus z squared dv. I'll see if I can even keep up with the units this time. I don't know if that's going to make it more complicated. I was able to figure it out afterwards, but let's just see if I can keep the units in place as we go along. So we have rho. Oh, and this is still a dv. Sometimes I want to do that and leave off my third one, so I'm going to have to keep that in mind so I don't do that. So we have x squared plus z squared dx dy dz. All right. So why don't we do y first? So we have rho y, and y is from, let's copy this down again. So y is from 0 to 3. And we have integral x squared plus z squared dx dz. So that's going to be obviously 3 rho integral z x squared plus z squared dx dz. So then we have 3 rho. I'll do the one on the left first. Oh crap, and I forgot to put my units in again. So this is 3 meters. All right. We'll try to keep up with this going forward. So I'll also integrate my x now. So I have still my integral z. I have x 3 over 3 and x is from 0 to 2 plus x z squared. X is from 0 to 2 is meters, and dz. So now we have 3 meters times rho. We have 8 meters cubed over 3 plus 2 meters times z squared dz. One more integral. So we have, and Rabbit says, why do you think it's releasing nickel, the comet? Oh, that'll just be whatever composition is. I mean, so my focus in my research, some of you may know, some of you may not, since you may be new to the channel. Like, subscribe if you haven't. My research is based upon stars. So all the elements that we have beyond helium and maybe some lithium are from stars, either the furnace in the core of a star or the explosion of a star in a supernova. And when these things either explode or they evolve to the point that they become a planetary nebula and they start releasing or exuding their atmospheres, that seeds the surrounding interstellar medium with those elements, and these things can contract and cool and become comets or whatever they're going to be. So just like how when the meteorites come and hit the planet, these meteors, even though they're coming from the Oort cloud or whatever they're coming from, they have iron and nickel, and they have things that's not from Earth as well, because that's just the stuff that was in the gas cloud, the dust cloud that formed the solar system. So the same thing happens throughout space. So it was just in a region of space where the star was a certain mass where it produced a lot of nickel, and either exuded it as a planetary nebula or it exploded and spread it through the part of the universe it was in. And that matter formed another solar system and cooled and, in a time, what could have happened that threw it out this way? Maybe there was a collision in the solar system that threw that particular comet out towards us, or maybe it was a collision of different solar systems or what have you. But something happened to give that mass that's been seeded with nickel from its star or from a previous star to its progenitor, and therefore it has nickel. So that's all it is. I would say it's not so much the amazing thing wouldn't be what it's composed of. That'll just relate to what mass of the star made the material that made the comet. The problem more interesting is its speed and things like that. Well, nothing moves against the sun's gravitational pull alone. So if an object is coming into the solar system, it's getting accelerated by the sun, and then on the other side is being slowed down. If you mean, I think you mean because it's going like this. Yeah, I guess that is interesting. So in other words, it didn't curve like that. It curved outward. Oh, I see. Okay, I have to think about that one. I don't think the planets will be able to do that. So if it curved like this instead of the other way, I'll have to think about that. So I guess some people might be thinking it might be intelligently um, navigated, but it could be a scientific reason as well. I'm gonna take a look at that image one more time. Not the image, but the whatchamacallem, the little illustration it had of it going through the solar system. You know, it's not. It's not going against the sun's. Let's look at the illustration one more time. It's doing what it should do. So, crap. I thought I saved that. I guess I did. So it's coming into the solar system like this. The sun's gravity is affecting it, so it's going like that, and then it'll go out like that. Here's so it's doing what it's supposed to do. So here the sun is accelerating it. Here is going faster because it gets pulled against the sun. So here is going faster. It bends around by gravity, and here it's starting to slow again. And by the time it exits the solar system, it'll be going about the same speed as when it came in because it got sped up and then it got slowed down. So it's not doing anything unusual. Right. So see what we have here. We have 3 meters, 2 meters. Now I just have to do the Z. Right. Seems like we're making some good progress. So we have 3 meters, rho, integral. Oh, we're going to go 8 meters cubed over 3 Z. Z is from 0 to 1, thank goodness, plus 2 meters Z cubed over 3, 0 to 1. This is times all of that. So this is going to be 3 meters rho times 8 over 3 meters to the fourth plus 2 over 3 meters to the fourth. So this is going to be what? 3 meters rho times 10 over 3 meters to the fourth. So this is going to be, tell me there's some way to simplify this a little bit. So making mistakes with my writing. Look good. If you see an algebra mistake, let me know. This will cancel. And the units are still, I have to think this is a denominator. So this will be 10 rho 10 meters to the fifth. And we know that this is going to be 0.5 kilograms per meter squared times 10 meters to the fifth. So IYY equals 5 kilograms per meters. Hold up. Oh, this is kilograms per meters cubed. About to say, hold up, I made a mistake because I had something. Okay, let's pick some alright numbers. I mean, these numbers are not so bad as long as I round up this to 0.5. It's not all that bad. So I'll just make this official up here and just make this 0.5. Right. Let's see if we have any questions. Do you know anyone with a live feed of it through an observatory? I mean, they say that the one in Chile has access, but I mean, we work with the McDonald Observatory. I had a professor that I worked with when I was still at UT who has a telescope in Chile, so he can get access to it. He has his own telescope he built out there. He's a very intelligent guy, very good at technique. I'm not a engineer person. I don't like to build stuff. Um, Thankfully, well, of course, that's why one of the reasons why I applied here at SMU because I wanted to do theory, not building stuff. So I'm like learning using the data that we get. But I'm sure there's people that do. I don't have access to it. Most of that data I have access to is from the ROTC telescope. I started to learn about it a little bit because my research deals with a lot of its data. Apparently, it's a telescope that's distributed around the world, which is odd to say, but it's kind of like there's different sites that has different versions of it, and we get data on stars from it. So it's pretty cool. All right, so we have IYY. Now let's do IZZ. We have this. And again, let me know if you have any questions as we go along. This should be different again because I made different values for the axes. So it's going to give us an interesting problem to solve to get the um, eigenvalues and the principal axes. And I find myself saying interesting now, like the physicists do. I used to hate when they said that because usually that means the problem is hard, but I guess it's starting to seem more fun to me. All right. So let's see what we have. We have integral v rho. And again, the Kronecker delta is 1 since we have zz. And now we have uh, x squared plus y squared dv. So we have triple integral rho x squared plus y squared dy dx dz. So we shall do the v first. Rho integral v x squared plus y squared dy dx. And z is from 0 to 1. Oh, crap. Now my easy one is out the way first. Right? So that means we're going to have rho, I'll just carry my units, 1 meter, integral, and x squared plus y squared dy dx. And let's go ahead and do y next. So we have rho, 1 meter, integral. So we're doing y. So y is from 0 to 3. X squared plus y 3 over 3, 0 to 3, dx. So now we have rho 1 meter, integral x. So this will be, 3 meters, x squared plus 27 over 3. And this is going to be meters. This is just meters. This is going to be meters cubed dx. All right. So now we have rho 1 meter. That's interesting. I like derivatives as well. I like derivatives and I like integrals, Rabbit. A lot of people don't, so it's good to see somebody else who do. So I think they're fun. I don't know. And of course, derivatives and integrals are how we got the majority of our technology, right? Because, um, cars, airplanes, dealing with acceleration, you have F equals ma, which is F equals m d v dt, which is, I drew an extra m equals mdv dt, which is m d squared x over dt squared, right? So that's derivatives right there. Oh, I don't want to do that. So, you know, that's the forces that we have on so many of our technology and things like that. And then if we're gonna solve this thing, right? We're gonna have ma, or you could say mdv dt equals whatever other force or whatever we having it with. So we might have mdv equals dtf, and then we have to do an integral over here. And well, of course, I will get the m on the other side as well, but you see what I'm saying? And then we'll end up solving for v of t in whatever terms, provided I put the m on the other side, just in case somebody watches and they don't see what I'm saying, right? So derivatives and integrals are ironically an integral part of our world and our technology. So pretty powerful stuff. Newton was cool dude. So now we have x. So we have 3 meters. X cubed over 3. X goes from 0 to 2 plus 9 meters cubed. X 0 to 3. So now we have rho 1 meter, and we have 8. Well, let me actually cancel the 3's here. A 3 there, a 3 there. So that'll be 8 meters to the 4th plus 27 meters to the 4th. So this is, hold on, that's a 2. Not 3. Crap. About to make a numerical error. Mess up the whole symphony of my magical math. So that's 2 meters. All right. So we're going to have rho 1 meter, 8 meters to the 4th plus 54 meters to the 4th. So that equals rho 1 meter, 62 times 62 meters to the 4th. So this is going to be rho 62 meters to the 5th. How 6 that's good numbers? That's because they're just whole numbers, and that's why it's working out so well. Maybe that's all it is. So this is going to be, who was the density again? 0.5 kilograms per meters cubed. So there's 0.5 kilograms per meters cubed times 62 meters to the 5th. So that's going to be, I'm going to plug the charger up momentarily. It's going to be 31 kilograms meters squared. And this equals IZV. So now we have the diagonals in the moment of inertia tensor. So this is a tensor, which is a matrix that's applicable. This image is still going off on the side of my head. It's just scratching me a bit. A little solar system image. Let me close this thing. So now we have the moment of inertia about the primary axes. So in other words, if I were to illustrate this, what we're talking about here, and I went over this a little bit earlier, but now we have some values to back it up. So let's go ahead and show that really fast. we said that torque equals IA, just like how F equals MA. And we have our values for I. So the idea is that, so this is IZZ. So if I made a torque here to move it exactly, and I guess technically since it's positioned there, no, that should be it. If I make a torque there, and this thing is situated so that the line here is tethered there. So imagine this is a tether point, and I'm putting torque to go in that direction, right? So it's tethered here. I'm pushing it straight ahead. So now it's spinning around that way. The resistance to the torque I'm pushing on it, because of the mass of this particle, will be 31 kilograms per meter squared. That's the resistance that it has to me pushing on it at that point, right? And the same thing goes for the other axes. I just did the Z because the Z value was right there. But any axis I put, I can look at my value for the IXX or the IYY, and I can see the resistance that thing will have to me pushing it around that axis, right? In the clockwise direction, right? So that's what that's telling us, right? So you can see that that sphere is only, well, I guess I can't really even relate this. I can't really say I've done a lot of pushing things around to think about how much they are. Like, let's think about a volleyball. How much is a volleyball weigh? I remember when I was in like high school, we had a game where we had like a pole, and there was like a volleyball tethered to the pole, and you like hit it around. So you like one person is standing here, and the other person is standing there, and you hit it around to that person, and they hit it back, and then you hit it back like that. That's probably the only thing I could think of where I'm accelerating something around with torque, because it's coming at me. I have to stop it and speed it up the other direction. How much does the average volleyball weigh? Let's see. See if we can get an idea of what this torque is. So a volleyball weighs about, 280 grams? Damn. This is going to be hard as hell to move around in. So a volleyball is 280 grams. That's 0.28 kilograms. Damn. So, yeah, so I'm thinking about this probably. How much did I make this thing weigh? 2 kilograms? Oh, crap. You would not want to play with this volleyball. This is like a lead weight or something. Yeah, we want to kill ourselves trying to knock this thing around the pole there, playing this game with it. Yeah, this is horrible. I mean, it is heavy. So this thing has a lot of resistance. It'd be hard to move this thing. And hold on, let me scroll up, see where I left. Derivatives. Yep, I love derivatives in equation. Yes, and integrals. Yes, so true. And we're talking about that, about Newton. And math is wonderful, and I love it. It's application of chemistry and bonding. Yes, so we have to take chemistry as physics majors. So I was very upset about it first, but they made the class very fun. Learned a lot, and now that I get into my astronomy stuff, I mean, that's pretty relevant when it comes to spectra and how the spectra is made and the chemical compositions of nebula and things like that we end up talking about. So yeah, I think chemistry was cool. And Mom says maybe FTFE can go on the ISS again and tell everyone about UN Atlas and go on the ISS again. Do you mean that Fight the Fighter actually went to the ISS, or you mean like the what do you call it? The overlay, like his background? And Rabbit says, "For my ass off, we'll be waiting forever with his fake ISS photo. High so lame." I saw his background before. It's pretty cool. Yeah, me and Fight the Fighter did a Fighter debate before. Sometimes I think about doing it again, but these people are such liars, man. These flat earthers, man. So I mean, I do like, I mean, want to be a professor, so I do like talking in front of people and talking about science, but people are so dishonest and manipulative, man. There's no point. But there is some fun to it, being that it's a public speaking event and I like that. But I don't know. I think about doing it again sometimes, but then I don't even feel like talking to those people again. But then I think, yeah, maybe it'd be nice. I don't know. Maybe I will again one day. But maybe I needed to get away from the nonsense for a little bit and decontaminate my thinking from the nonsense of dealing with those people for a little while. Maybe I'll go back after a bit. All right, let's go ahead and get some off diagonal things. All right. So the good thing is these things should be symmetric, right? So those should be the same. We shall see. We'll look at it and see. So we'll say I, X, Y. Does this equal I, Y, X? So we know this is going to be integral V rho. And then we have R squared Kronecker delta XY. And this is going to be minus XY dV. So this is just thanks for saying. All you have to do is look at the last one I talked to on my other channel, Flatzoid. Like, I had a debate with him, and I called him out on his thermodynamics nonsense. People clearly don't understand thermodynamics. And at the time, I didn't take the class yet. I didn't have a good understanding of it as well, but I knew enough to know that it doesn't mean the Earth doesn't have an atmosphere. And I called him out on what his equation was, and he was like avoiding it like they dishonestly do. And I called him out on that, and he accused me of being condescending. So what I did was I contacted Modern Day Debate, and I said, look, I want to debate him on thermodynamics because I was taking a class the next semester. So I was like, okay, study on it a bit during winter break and talk to him about it. So I did like a quick reading. But Modern Day with Debate was like, oh, this is too nuanced a topic. Or we don't want to do this topic. So I went to him directly and I said, look, you don't want to do it. Why don't you just come on my channel and you could explain, what you say I'm wrong about or whatever. And the video is on my channel. Maybe I'll post it here so if anybody interested in talking about it. So he came on the channel, and the whole time he was trying to avoid explaining, which was his whole point being there. But of course, they can't explain. But he said I was being condescending and stuff like that. So I gave him the opportunity. Then I challenged him for it, and he did the whole, I don't know, whatever nonsense spiel they do. You can't have gas without a container or something. So then I challenged him to, okay, since that's all you need, let us know the average efficiency of a power plant, because we get the efficiency of power plants from the first law of thermodynamics and the second law of thermodynamics. I have to actually calculate that in class, the efficiency of a power plant. I didn't have the class by then, but I was reading through the textbook a little bit, and I knew that was a thing. So I asked him to do that since you're such a pro and you don't need an equation. So then he comes up with an equation magically, right? Of course, he has to avoid that now because I asked him to actually back up. So I asked him to find the equation, show me the equation in that paper, and show me that it does what you say it does. And I didn't push really hard because I wasn't trying to be computational. It was for him to explain, but he avoided that. And I challenged him to do something else. And the first thing I should have did was trust him at all. Like I gave him at least a decent amount of trust that he was actually presenting the second law of thermodynamics equation. I was new to it. I thought he was just writing it in a different form. He asked me if I was familiar with the equation. I was like, yeah. And but obviously he was lying about the equation. That's why he was so excited when he said, he said he's familiar with it. I was like, okay, so that was a trap question, right? Turns out when I looked at his review of the talk later, he lied about the paper. Whatever paper he did, he must have just Googled up a paper, and he admitted on his channel, the equation wasn't even in there. He was looking for it because I was scrolling trying to find anything. I didn't see it. He was making fun of that. And then he said something else, like he said, oh, he was just admitting to being dishonest, right? So it's like, it's just amazing. Let me find a link to that if y'all didn't see it. I'll post it here. And that's the last time I talked to a flat earther. I'm like, this is just the biggest waste of time ever. And I guess to a certain extent, I was interested in trying to actually educate these people a bit. And but most of them just don't want to be educated. They're dumb and they want to be dumb. And any attempt to dissuade them of their stupidity will be met with dishonesty and manipulation. And so I guess as long as you understand that, I guess it's fine. Like if I ever talk to them again, I'll just go in with that understanding. And maybe that'll make a difference in getting frustrated dealing with them. So I found those videos. I'm going to link them really fast, and then I'll continue with the problem. But everything I just said, you'll be able to see it live. You can let me know if my rendition of it is incorrect or something. Right, so here's the live challenge where the original talk was where he put the fake equation in and lied about that. This is my initial. Oh, hold on. Let's click. This is my initial review where I review what we discussed. And here's the one where I believe I found his video talking about the lies he did and being amused by it, being happy about his lies and deception. He openly admits it. And the thing about it is, the flat earthers are like, NASA lies and we don't trust liars, and they follow people that openly lie. So I guess it's fine if you lie in honor of flat earth. If you lie in support of flat earth, then lying is apparently a very good thing to them. Is amazing. I'll put these links in my channel as well. In this channel, I think it's worth seeing. I mean, one of the reasons why I still think about and engage is the psychology. A lot of people may not know this, but I was actually going to be a psychology major. So I was going to be always physics. But I was going to be physics and something else. So I first was going to be physics and math. Then I realized I hate mathy math. Like, I like math, but like straight up math, like all these proofs and stuff, I hate that. So I was like, I can't spend my life doing that. No. So I was like, no. So then I was going to be physics and psychology, but psychology has become. I'm still updating these links here. Psychology has become overrun with this gender ideology and critical race theory stuff. So like, I don't want that either. So then I knew I liked astronomy, so that's why I made my second major astronomy. So I have a bachelor's in physics and a bachelor's in astronomy. So I have those linked there. Let me close some of these windows here and I'll confirm up with the proper links. So that one is that link. To it's the second view. The first review. Okay, A got that one. And the original one. Oh, yep, they're all there. So I think it's worth seeing. I think it's worth seeing just to see the psychology of this person and the psychology of the people that follow them, who declare that NASA lies, even though the evidence is there and you can check it for yourself, but then openly follow an admitted liar. It's amazing. All right, let's keep on going with this problem. And this is, was it I? No, hold on. DV. Oh, hold up. I might have to close this thing and reopen it. Sometimes it bugs. Oh, that's what it is. My power's getting low. I said I was going to plug this thing up. Thankfully, I remember it before the battery died. Thanks, man. I appreciate you giving him a like, Rabbit. Appreciate that. So I plan on making a video there soon. That was mostly my flat Earth debate channel for a while. So that's why I ended up just doing pure science here, because I got tired of flat Earth just coming trying to say stupid stuff all the time. And here they like straight science, and they're like stay away. So I haven't had one here yet, because I only talk about like real strong science stuff, not even just beginner stuff like I used to do on that channel. But I will make a video there again sometime talking about something. Yeah, it's like water on the witch. Talk about some real math and science. All right. So now this thing is plugged up. It should start working properly again. And let me turn this the proper way. There we go. And this is uh, why sometimes this pin, I have to restart the program. I try one more time. Maybe the pin is getting uh, issues with the mat. Like the pin is getting upset with the integrals. Like, hold up, should I be doing all these integrals like this? I'm gonna close this program and reopen it. I know sometimes it like not updates but backs up, whatever backing up, and sometimes that causes it to freeze as well. So it might have been backing up. Let's do it. I'm gonna try one more time. I'll just let it finish backing up. While it's backing up, we'll still have. No, I closed the thing. I was about to raise up the comment video again, but it's only take a moment. All right, seems to have finished backing up. This is a big file that I have this in. The pin is still not working. It says it's connected. Okay, maybe I need to just restart the pad. I'll restart this pad and see if it works. Those anti-social social scientists, you mean? Man, it's amazing. You know, I actually saw a good debate the other day. Because I was sometimes when I'm in class or when I'm doing homework or whatever, and I run into some piece of data, it reminds me of them because of the stupid stuff I know they would say about that particular thing. And a debate between MC Toon and McGlowface and Allen, who I had destroyed with PhD Tony. So I enjoyed that debate with PhD Tony. He's one of my favorite flat earth debaters. And and who was it with? It was me and PhD Tony versus Allen and Toby. I think his name is Toby. And but so Allen was debating again, but this time it was with Shane, who ironically was the one who was coaching Allen and Toby to be dishonest in his debate with me and PhD Tony. Whenever there was a moment when one of them, Allen, I believe, was like moving his windows around, and he mistakenly shared a window he didn't want to share. And it was Shane saying, "Just make him mad. Just. It's all about making him angry or something like that." So, and this guy is on debating. It was amazing. But it was a good debate though. This was after MC Toon came back from Antarctica, so he was really laying that Antarctica evidence on him. It was pretty fun. It was pretty fun. Yes. Uh, MC Toon really likes that. There we go. Nice working again. Likes trapping him and stuff. So let me let this show while I get this showing again, so I have to pull with everything. Boom, boom. Here. Right. The pad is working. I'm not sure why it stops sometimes. I have been going. Maybe maybe the battery of the pen is getting low or something, but it says 79%. Like when I plug it up, it shows the battery. So I don't know. All right, let's keep it rocking. And this is DV. So now we're going to get the off element ones, and then we'll be able to do the principal axes and see how that looks. All right. So we're going to have integral, rho. Now, this is where this comes in. This is x equals not y. So this Kronecker delta, xy equals 0. So that means this entire term right here zeroes out. Do y'all see that? So now we have rho integral volume. Put the rho on the outside already. And this is negative xy dv, right? And if we look at this, if I had yx, I mean, it will be the same thing. It'll just be negative yx dv. So as we can see, the all diagonals right there it will give us the same. So there's some symmetry. Like if I were to put some torque not in the x direction or y direction proper, and not even sure how you would put it in both directions, since it's, I guess technically you would put it like this. Like if I was to put some torque this way, but that's around the z. I'm not even sure how you would put torque in the off-axis direction. Right? Trying to relate that to Professor about it, I guess I email. But how do you put torque in the off-axis direction? Because the y torque and the x torque equals 0 in the positive direction. I guess it must give us a negative. Let's see what value it gives us. It must be that this gives us a negative, and the negative would have it be torque in the x direction for one, and negative, like let's say negative y direction for the other one. So maybe that's what it is. All right. But we shall see. We shall see. Let's do this one and see what this ends up being. So we're going to have equals, let's write it over again. Integral, negative yx dx dy dz. And I'll copy this down again. And I'll also copy this down. Boom. Right. So we have this equals rho. Let's do z first. And z goes from 0 to 1. So let's just put that there, 1 meter. Integral negative yx dy dx. So, and then let's go 1 meter rho. Let's go y. So we have negative y squared over 2. Y goes from 0 to 3. And then we still have x dx. So this equals 1 meter rho integral x. And this is going to be what? Negative 9 over 2 x dx. And hold up, what's my unit? Meters cubed. So I'll just take the meter out. So that'll be meter squared since it's squared. So I'll just bring that out so we have meters cubed on the outside. So here we have 1 meters cubed rho. 9 over 2, x2 over 2, and x is from 0 to 2. So then we have row 9 over 4 times 4. This is squared. The 4 is meters squared. And then we have meters cubed. So again, this is meters squared here, meters cubed in the front. So we have meters to the 5th again. And the 4 cancels, which is nice. So now we have 9 row meters to the 5th. So IXY equals IYX equals 9 over 5, because it's 1/2 kilograms meters squared. Because rho is 1/2 kilograms meters cubed. 5. So, okay. A little more complicated, but it's not bad. All right. So, again, this is the off diagonals there. These are the diagonal ones here. Oh, let me make sure I put my XX. All right, so we're almost done. All we need now is 2 more off diagonals. Oh, it's going to be a complicated matrix. Some good practice, though. Why don't we do the XZZX? So we have IXZ equals IZX, which equals integral rho r squared Chronica delta ZX minus ZX dV. So again, this Chronica delta will be 0 since they're not the same. So we're going to have integral rho negative z x squared dx dy dz. Now, the thing is, the integral, hold up, not a square there. The integral is the same, except the bounds are different. So I would jump in again, but I don't want to mess something up, so let's go ahead and do it. So we have y is from 0 to 3 right here. So we're just going to have rho 3 meters, since y is the odd man out. Integral negative zx dz dx. So this is going to equal rho 3 meters. We'll do z since it's on the left. We have negative z squared over 2. Z is from 0 to 1. And we have x dx. So this is going to equal rho. Oh, of my negative. Just realized I dropped negative. I was 2. I dropped my negative right here. You see it? So last place I have my negative. So this is a negative. This is a negative. And when I put in my, okay, so this is a negative. Okay, so it was as I suspected. We do have a negative. So down. Have to think about what that means. The negative over the whole thing. So it's going counter to the axes, counter to the xy axis. So, oh, this is what it means. So if I were to push this thing this way so that it goes around the xy axis here, right? Positive is this way. Could that be what it is? Yeah, it must be what it is. So I won't say definitively, but it seems likely. Let me email my professor and ask about that. Or I might just look up a video somewhere. Maybe I'll find a video on it. All right. Let's keep on going. So we have rho um 3/2 meters cubed negative. Then we still have integral x dx. We did the v first. Excuse me, the y first. Dx is making sure I didn't make a mistake somewhere. Y is 3 meters. Z is 1. We're left with the x, that's 2. I think this is right. If I made a mistake somewhere, let me know. So I have negative rho 3/2 meters cubed x squared over 2, 0 to 2. So this is going to be negative rho 3/4 4 over 4 meters to the fifth. When I bring in the meters squared here and the meters cubed there, I'm multiplying the 3 to the 2 there. Then I just have the 4 from the integral. So this is going to allow me to cancel the 4's here. So then we have negative rho 3 meters to the fifth. And we know that that's going to be 1/2. So we have 3/2, negative 3/2. Kilogram meter. It's interesting. You know, we have those off diagonal elements. So let's think about this. Yx is going to be longer than zx, right? Because if you have square root of 2 squared plus 3 squared, that's going to be square root of what? 13. That's for the xy. But zx is square root of 2 squared plus 1 squared, which is square root of 5 squared. So it stands to reason that the magnitude of the yx1 will be bigger than the xz1. You see that? The xy1 is bigger than the xz. So it seems like we're onto something. And Mom says, is there a computer application that can solve matrices within its programming? Yeah. You can go to like there's Wolfram Alpha, there's Symbol Lab. They're pretty good, I think. So one of my homework assignments, we have like a complicated matrix. I just put, solved in, but it kind of got it wrong too. You gotta be careful. I did it and it didn't quite solve it right. I knew because the matrix, like normally you get, I don't know. I guess it's I don't know what to say. Its notation is bad. I don't know. I just ended up doing it by hand anyway. Like I solved it there and it gave me something. I guess technically it was right, but the way it notated it was not correct. But when I solved it myself and I compared it, it was like, okay, now I see what they're saying. Maybe you just got to get used to the notation. But yes, you can go there and it can do it. You can get like the eigenvalues and stuff. But I'm gonna have to practice doing it by hand because we got to do it by hand on our exams. But I mean, I don't think she's gonna give us a super hard one, but we'll see. All right. So I think that's that. Let me make sure I didn't mess anything up. Yeah, I think that's good. And the xy is bigger than the xz because the radius is bigger for the xy than the xz. So it will be harder to move it around that bigger area. That makes sense because the I is mr squared. So the bigger the r is, the harder it is to push. So right now it's making sense. And again, this is xy, xz. All right, let's keep on going. So now we have just this last one. And we shall do some matrix magic, like Mom was mentioning just now. We'll see how that works. It should give us the same value. Let's look at it and confirm. So we have I, Y, Z. Oh, not Friday should. Yes, this does equal. We have I, Y, Z equals I, Z, X, which equals again integral rho with respect to the radius from the center of rotation, r squared, distance from the center of rotation, Kronecker delta, YZ. So again, that's in the green quadrant here, YZ and ZY, minus YZ and DV. All right. So what we're going to do is we're going to integrate like so. So we'll say integral. This is going to be 0 since this doesn't match. We're going to have rho negative YZ dx dy dz. And again, we have our values. All right. So why don't we do what? X first again? Because X is well, this time the X is the Iron Man out, not Y. So we're going to have an axis from 0 to 2. We're going to have negative, about to forget my negative again, rho 2 meters, integral Y, integral Z, uh, negative Y, Z, dy, dz. I think that's good. Negative rho 2 meters. Y is on the left, so I'll just do that one first. Oh, put a double negative there. It's not good. We have rho 2 meters, still integral z, negative y squared over 2. Y is from 0 to 3, z dv. So this is going to equal negative rho 2 meters, still the integral z, and we have negative 9 meters squared over 2. So the twos will cancel here. So we have z. So we have what? Negative rho. Still putting a double negative here. So we have a negative rho 9 meters cubed. And then this thing d. All right, seems like we're good. Rho meters, meters squared, meters cubed. The negative is there. The twos cancel 9. So you have your z integral dz. So then we have negative rho 9 meters cubed, z squared over 2, 0 to 1. So now we have negative rho 9 over 2 meters to the fifth. So that's just 1. Okay, that looks good. Meters per meters cubed. So then we know that this is the 1/2 kilograms per meters cubed. So I got to divide that by half again. So that'd be -9/4. The meters cubed squared cancel. So kilograms meters squared. So let's look at this. So what color did I make that one? Purple? Oh, green. This is green. So well, this is I, Y, Z. So 3, 1. Let's see where this adds up to. So now we have Y, Z. So that's square root of 3 squared plus 1 squared. That equals square root of 4, 5. No, square root of 10, I bet. And, right? So that's in the middle between these two. Okay. So this value should be between those two. Hmm. So this will be, the fractions are a bit hard to tell clearly. But 9/4, we right sort of a, what's we call them? So what? So 2 squared, 4, 9, 4, 5, 10. So we have the biggest one is XY is bigger than YZ is bigger than XZ. So let us see if that's the case. Matter of fact, let me write the whole matrix. We could do this all at one time. So we have that, and I've already written the sort of template for the matrix setup. Let's go ahead and look at this thing at one time. We're going to need to do this anyway to solve for the eigenvalues. So we have this. So we have going to simplify this by few adjustments here. So we have kilograms meters squared on the outside. So we have 4, 9/4. We have 3/2, -3/2. We have -9/5, -9/5. We have 8, 5, and 31. 8, 8, 5, and 31. Right. So this is the matrix of the moments of inertia for this mass placed at point 231 around the X, Y, and Z axes and the off axes, right? So we see that X, Y, Z, X, Z, and let's see if that matches. So the smallest, 3/2, yeah, because 3/2 is 1/1/2, and YZ should be the next one. 9/4 is 2 1/4, and XY, crap, it breaks down right here. I have to think about that. I made a mistake on a calculation somewhere, or maybe that's just the way the inertia is. Uh, the XY plane, I figure it should have a relation. XY, XZ, and YZ. XZ. Y, YZ, XZ. All right. Well, I think about that. The values seem like it matches up here. So what will cause the inertia around? Maybe I should copy this down to get a better deal. So what will cause the magnitude of the inertia around the ZY axis to be bigger than the X axis, or vice versa? Different. On the XY axis, there's a certain distance away from the axis. You know what? It could be because the Z is so small here. That makes a difference. The ZX versus the ZY. So the magnitude just must not play a part. And you can clearly see the XYs are a little bigger. ZY, X. I have to think about it. But physics is sometimes not intuitive. All right, let's keep on going. We'll assume that this matrix is right. It could be my approximating it as a sphere, even though I don't think that should make a difference. Really? I mean, approximating it as a point, but let's keep on going. So what we need to do now is, the idea is that my matrix I, if I were to multiply it by a principal axis vector, is going to equal some lambda times the same vector. And this is linear algebra. So that means that I omega minus the identity vector times lambda omega equals 0. So we can go I minus identity vector lambda omega equals 0. And what this does is allows us to get a eigenvalue, which is what this lambda is, to match this eigenvector. To solve for a particular vector and value that makes this relationship work. So the thing about this process is I'm going to have a sort of unique solution only when the determinant of I minus identity vector lambda equals 0. So I need this determinant to equal 0. So it means I need to find what lambda will make this determinant equal 0. And then I'll have a viable solution for lambda to work with the vector we need to find. So that's the process that we go through within the algebra process. We find the eigenvalue, and then we find the eigenvector. In this case, the eigenvectors will be the principal axes, like the main axes of rotation, which I still have to learn the concept, the basis of the concepts of, but I think I know the process pretty well. All right. So I'm going to copy this down without, and let me see if I can simplify this a bit. Let me think. So all right, here's what I'm going to do. I'm going to say I equals 20 over 20 kilograms meters squared 8 over 5 over 2 negative 9 over 5 5 negative 9 over 4 3 over 2 negative 9 over 4 31. And I'm going to multiply the 20 in. So I have I equals 1 over 20 kilograms per meter squared of 60. And let me make sure I don't mess up my values. Trying to do all this in my head. We have 20 times that's 36. And 20, that should be negative 30. So it's 20 divided by 2 is 10. Right? This would be negative 36. 5 times 20 should be 100. 20 times 9 over 4, 45 negative. If I made a mistake, let me know. 45, 31, T is 620. Right. Will this make it easier? I would hope so, since it's whole numbers. But we shall see. Right. So I have, let me just look one more time. Everything looks good. I checked it. Really in my head real fast. And if you have any questions, let me know. Let me just check my windows a bit. Everything seems okay. All right. So now we can get I identity vector lambda equals 1. And I can easily copy this. We have 160 minus lambda, 100 minus 620 minus lambda. So now it's going to get a little bit more complicated. And welcome who joined. Let me know if you have any questions or comments. Please like, subscribe if you haven't. So now we're going to get the determinant of I minus identity vector lambda, which is that. So I think, so there's two ways you can do this. Sometimes it's better to do one way or the other. If you're interested in seeing both ways, let me know. I think I'll do the multi-determinant way. But let me know if you want to see the basket weave way. I don't mind getting some practice on it. So 160 minus lambda, which is here. And we're working with this one. So we're going to be 100 minus lambda, 620 minus lambda, minus 45 squared. So this equals, so we're going to have minus negative 36, so plus 36. So we're dealing with 36 and these four. I did the minus, so I'll do it the regular way. So we have 45 times 30 minus plus 36 times 620 minus lambda. Let me know if you have any questions. So I did the minus on that one, so I did it the opposite way. Yep, so we're good. So I'll do the plus on this one, which is the minus 30. So these are dealing with this one and these four. Plus was minus 30. So you have 36 times 45 minus, which is plus 30 times 100 minus lambda. All right. So we have that. And to keep my notation consistent, let me make these brackets. So divide this out. Whenever else I just put this in the calculator. Definitely be easier. Chuckle, let me know in the comments. Oh, good. No questions. No questions so far, Mom? Would you like to see this multiplied out? Or you just want me to put this in the calculator to save time? I could just put this in the calculator and save time, or if anybody would like help with calculating this out, I could do it, calculating it out as well. I'll give somebody a second to respond. Here, I might make an issue. Okay, yes, let's multiply it out. I was about to say I was scared I'll make an issue with the calculator anyway. So that works. All right. So this is what we have. We have 160 minus lambda bracket. And let me make this 2 better. So I have 100 times 620. That's 62,000 minus outer and inner 720 lambda plus lambda squared. And this one we need to put a bracket there. Minus 45 squared, which is 2025, plus 36. And now we have 45 times 30. So that's 1350 plus 36 times 620. That's 22,320 minus 36 lambda. And we have minus 30. Now we have 36 times 45. So that's 1620 plus 30,000. No, 3,000. How many zeros is that? Yeah, 3,000 minus 30 lambda. All right, so it's not so bad. Then top line, I'm going to distribute the 160 first. Big number. So we have 992,000 minus 720 times 160, 115,200 plus 160 lambda squared minus 2025 times 160. That's 324,000 minus, now I'm going to multiply the lambda in, lambda 62,000 plus 720 lambda squared minus lambda cubed minus plus 2025 lambda. First line plus 36 times 1350, 48600 plus 30 times 22320, 669,600 minus 36 squared lambda, 1296 lambda minus 30 times 1620, 48600 plus 30 times 3,000, 90,000 minus 30 squared lambda with a minus, so that's plus 900 lambda. All right, not so bad. Let me know if you have any questions. So let's do this thing. So I'm going to have 992. Maybe I should just find these numbers. They're up in the calculator. 992,000. That's this one. Minus 115,200. That's this one. minus 324,000. That's for this one, plus 48,600. That one, plus 669,600. That one, and I think that's all the free numbers. Just a few. Minus this one, 486000, and plus this one, 90,000. So that's, I'm going to just call this number alpha. Alpha. We're going to say alpha equals 10240400. So this is alpha. And then we have the lambdas plus, so we have the 900 lambda there, 900 minus 1296 lambda, um, plus 2025 lambda, and lambda here, 62,000 lambda. Let me know if I missed any lambdas. I don't think I did. So that equals beta equals 60371. All right. Plus beta lambda, and plus, now we're going to do the lambda squared. So we have 160 lambda squared. Let's type that one. Plus 720. On the 2 lambda squared. I don't think I missed any. Right there. The lambda squared from when I multiply the 160 here. Excuse me, when I multiply the lambda here, that's a 720. And there's the lambda squared when I multiply the 160 here. So I guess that's it. This is an unusual problem, so I'm not familiar with the pattern that's going on. But I think that's it. And they're both positive. So I have, we'll say that gamma equals 880. Plus gamma lambda squared minus lambda cubed. All right, so then we have that worked out. So now all we have to do now is factor this beast of this. I need to do a calculator for. This is like crazy numbers. I'm sure we won't have anything like this on the exam. But just looking at it, how might I try to factor this the normal way? It's a good idea to guess one of the ones that we had before. Why don't I show y'all some long division? Would you like to see long division, Mom? Or would you like to see this one in the calculator? just calculate this one out at the same time. I could do some long division and guess that 160 is one of them. It has worked on the homework problem before. And divide by 160 and see if the long division pans out, divides equally. Or I could plug that in to the calculator to get the eigenvalues. Maybe I should plug it in anyway just to see if it gives me a good value, and I can still check it out and do it manually as well. Let's just see what the calculator says. 240 400. Awesome, Rabbit. I'll do some long division. Let me plug this in to make sure it at least makes sense. Because I may have made a mistake somewhere with all this algebra. X plus 880 x squared. So the calculator gives me a good value, and I know that it'll add up to something good. What did it do? We need to go to a different calculator. Hold up. So at least make sure I'm on the right path. So I won't be long divisioning needlessly. We have 1 0 2 4 0 4 0 0 plus 6 0 3 1 6 0 3 7 1 x 8 0 x squared minus x cubed. All right. So it looks like this does not give very easy eigenvalues, but I still want to do the process. So why don't we do this? I'm going to change up the numbers a bit, because again, I just guessed these numbers. I just pick numbers. So the numbers here ended up being fine, but these numbers here are just craziness, and you're not coming up with, like, even the online calculators are not finding good, like it's a decimal basically. Either I made a mistake on something or it's just very bad numbers. So I'll do the long division, but what I'll do is pick some easier numbers to long division with. So let me use this I'm going to change my values of alpha and such until I find a good combination. And then I'll do the long division on that. Close. Why don't we do all right. So I found one that I know works. So this is what we're going to do. We're going to say alpha is now defined as 36. We're going to say beta is now defined as -9. we're going to say, and actually, I want to say this is negative 36. Beta is defined as positive 9. And we're going to say that gamma is defined as positive 4. And I'll put a negative in the front. So I'm trying to make this not too easy. Make this out. We're going to have negative. Let me just do it like that. X cubed or lambda cubed. We need to have one of those negative. Hold up. You're going to have negative lambda cubed plus 4x lambda squared plus 9 lambda 36 equals 0. So we're going to have this. So that means that alpha equals negative 36. Beta equals 9. Gamma equals 4. Check and make sure this is good, and then we'll go ahead and get started. All right, here we go. Thanks, Rabbit. I appreciate it. I do try to be. All right, so we're going to solve this thing. So we're going to imagine that these crazy numbers that I picked, which was actually fun to do for the first part, but we're going to imagine that the numbers I picked ended up with being this, right? So, and now we're going to do some long division to solve this thing. So I'm going to multiply both sides by negative. So I'm going to have lambda cubed minus 4 lambda squared minus 9 lambda plus 36 equals 0. So what I need to do here, making sure I wrote the numbers right good, I need to try to find out what I can factor this into to get what I need. So one of the things we can do is we can guess. I see there's a 4 here. I'm going to go ahead and guess. And this might be a wrong guess, but this is how you do it. You guess. I'm going to say it's going to be plus 4 and see if it works. So lambda plus 4. So I'm going to be dividing this into lambda cubed minus 4 lambda squared minus 9 lambda plus 36 by long division. All right. So what we do is I take this first number, I divide it into this first number. This is lambda squared. So now I have lambda cubed plus 4 lambda squared. Then I subtract this entire thing. I have 0 minus 8 lambda squared. So we know that's not going to work because it's making things worse. I had a negative 4 lambda squared here, and now I have a bigger number, all right? So why don't we try lambda minus 4? And I'll just copy. The rest is the same. I'm going to try dividing this now. So I'm going to have lambda squared, because again, lambda cubed divided by lambda gives you lambda squared. Just dividing the first thing. Then I multiply it out. So I'm going to have lambda cubed minus 4 lambda squared. I'm going to subtract this whole thing. So now I have 0 plus 0. I'm going to bring down my 9 lambda negative from there. So whatever is there is just brought down. Now I'm going to divide again. So this is going to be minus 9, because if I multiply negative 9 by lambda, I get my negative 9 lambda back. And I'm going to actually bring down this plus 36 as well. And negative 9 times negative 4 is plus 36. So then I will subtract this entire thing. So then I do end up with 0. So that means that when I divide lambda minus 4 into that, I get an even lambda squared minus 9 out of it. And it still equals 0. So this all was the math to long divide the first guess, right? And speaking to what I mentioned earlier, I picked one of the numbers that was already there and sort of guessed that that could potentially be 1. And then it just tried the plus and minus of that. Or it could have guessed a 9, which would have gave me a wrong answer as well. But, I guessed the positive 4, went to the negative 4. If that didn't work, I would have guessed a positive negative 9. Maybe I would have guessed the multiple of 36, which ironically both of these are. If I'm looking at that correctly. In fact, they're multiples of each other. But the 4 actually worked. So that's a good way to get started there. Now, I'm going to look at this. This is easier enough to solve for. This is lambda minus 4. And this is going to be lambda plus 3, lambda minus 3 equals 0. Because this will give you lambda squared plus 3 lambda minus 3 lambda, which will cancel, and then minus 9. Right, so we have this factor, right? So now I know my lambda terms. So we're going to have lambda minus 4 equals 0, or lambda equals 4, lambda plus 3 equals 0, or lambda equals negative 3, or lambda minus 3 equals 0, or lambda equals 3. So any one of these values for lambda, if we plug it into the initial equation here, it'll give us 0, because we solve for lambda in that way. So these are my eigenvalues. These are the eigenvalues that make this determinant equal 0, which means these are the eigenvalues that gives us a unique solution for this matrix. Okay. Now, the thing is, the matrix doesn't line up anymore since I picked different numbers so that we actually have a eigenvalues that's not a bunch of decimals. That would have just been craziness. So, but perhaps I could still solve it. Not sure I know how to go backwards from a vector thing to, maybe I can. See what I can do here. One way this would work is if I minus lambda with this equals I think lambda minus 3, lambda plus 3, and the forget which way it is in there. No, it would have to be the way it is right there. So it would be negative 3 minus lambda 3 minus lambda. So I'm trying to still get the minus lambda iteration going on. And 4 minus lambda. And if we had zeros everywhere else, this would work. So let me check this. I can just look here actually. So if I move this around, this will be 0 equals 4 minus lambda. We got that there. And this will be 0 equals negative 3 minus lambda. Got that one. And this will be 0 equals 3 minus lambda. All right, so that should work. And this should give me the same lambdas. 3. Yep. All right. So let's say that was my matrix. Let's say my original matrix was I equals negative 3, 3, 4. The process that we did would be the same. Just my numbers would be different. And these numbers would just be not a whole bunch of decimals. Generally, we'll never give you problems in an exam or anything with decimals. Even in the homework, they didn't give us decimals. They're going to just guess those numbers. So it'll be like this. This will be my I minus lambda. I will take my determinant still of that. So it'll end up being, and I said I might do the basket weave method. This would be the basket weave method where I just take the negative 3 minus lambda times 3 minus lambda times 4 minus lambda. So then we're back where we were before, where negative 3 minus lambda equals 0. So lambda equals negative 3. 3 minus lambda equals 0. So lambda equals 3. And 4 minus lambda equals 0. So lambda equals 4. So now we've basically caught up with where we were. Just the matrix was a bit different. So this is our new matrix now. So now what we have to do is we took the determinant of this to get our eigenvalues, which we have here. So now what I have to do is go back to this equation, which is the original one that we had here. And I need to actually plug those values in and solve for omega. So I got my eigenvalues. Might be slightly confusing because I changed the numbers a bit, but let me know if you have any questions. I'm going to go back to my matrix here. All that is just the matrix. And now I'm going to have omega 1, omega 2, omega 3, which is just taking my omega and putting it in vector form. So this is this. This is this equals 0. Except now I have definite lambda. Oh, what lambda stands for. So lambda is basically the values that makes this equation be true. So in linear algebra, it's basically about finding values that takes a vector in a certain space and just stretches that vector when you apply it by a certain matrix, right? So imagine that I have a vector space. Let me just make some room here. Let's imagine that I have a vector space. This is X, this is Y, this is Z. And let's say that I have a vector in this space, a vector V. And what these matrices do is the matrices will transform this vector. So we've seen a 9-point vector already. And so these matrices, what they will do is I will take this vector here and I will multiply it by this matrix, and it'll give us another vector. it'll give us another vector, let's say W. But there's special vectors, proper vectors, which is the German for it is eigenvectors. And there's special values or eigenvalues, proper values, where this new vector is just a stretching, and maybe let me write it differently. This new vector is just a stretching of the old vector. So if I apply this matrix to this vector, and all it does is just stretch this vector or shrink this vector, that means that this vector is a special vector called an eigenvector, and lambda is a special value called an eigenvalue that is output when I put this particular matrix with this particular vector. So that means that this eigenvector is an eigenvector of this matrix, and its eigenvalue, this eigenvalue here is an eigenvalue of that matrix related to this eigenvector. And right now it just seems mathy, but when you do things like quantum mechanics, and you're trying to find details of different states, this comes into play, right? Or when we're trying to find, in this case, we're trying to find out what, so I have this particular mass, what was my original, I had this particular mass, at this particular location, and right now we're trying to find out what vectors are the primary vectors that this mass will rotate around. Given this mass, given this original position, what vectors are the prime vectors to rotate this thing around where it rotates, and if you rotate it in that way, it won't alter. Like, you could have a spinning top, and if you spin it very, very fast, it'll stand up and not wobble at all. Like, no matter how fast you spin it, if it's a perfectly balanced top, it'll spin perfectly. So that means that this vector here is an eigenvector, because the top can spin on that vector, that vertical vector, and not wobble. So that's what we're finding for this block. We're finding what vectors can this block rotate around and not wobble, and these will end up being eigenvectors, literally vectors in space that this thing can rotate around and not wobble. And we have to find the eigenvalue first to find those eigenvectors. So you may not realize how much this plays a part in things, but like right now we're doing momentum, and anything that has torque has momentum. Engines have momentum. Power plants have momentum. The turbines. Solar? What do you call those things? The blades, the fans. I forget what you call them. But those solar things where there's a big fan that's swirling around in the wind. Windmills, not windmills. I forget what it's called. But you know what I'm talking about. All of these things use momentum, which means that moment of inertia can be involved, which means that not turbines, but crap. Let me look it up. And I'm gonna be thinking about what this word is. It's a particular word. Solar farm, wind. Oh, let me see. Solar farm, a blade. I know. All about wind energy. Don't worry about it. I'll just find it another time. It's not a big deal. But suffice it to say, whatever those blades are called, whatever the official scientific name of those blades are, all of that stuff uses moment of inertia. So you can apply this stuff to that and figure out, how much power you can get out of so much inertia, out of so much wind, or how difficult it will be to get power. If this blade has a certain moment of inertia and there's no wind and it's stationary, how strong does wind need to be to get that thing moving, right? So you're going to have to take that into account, because if you make this blade with this humongous moment of inertia and you put it in a location where the wind is only blowing so fast, it's going to be a problem. You're never going to get any energy. So you have to understand the moment of inertia to know what's going to take to get that thing spinning. And you could do that by doing a problem like this, where you get the moment of inertia around that axis, and And the eigenaxes will be, of course, the axes of the fan. So that'll be an eigenvector, right? You have the fan here, and the blade is there, spinning in this way. So this vector will be the eigenvector, and you can do some calculations around that to see, but you get the idea. All right. So now let's go to this problem here, and let's actually find the eigenvector. So what I like to do is I like to multiply it out first. Let me just copy it down, put a lot of extra stuff. I'll just leave it there. This is a vector of zeros. Yes, science is exciting and clever. I mean, all our technology is based upon it. I mean, the thing about it is when you're an undergraduate, it just seems like you're just doing stuff just to do it. When you start to get to, you're getting your bachelor degree, then you start doing applications. But in graduate, there's a whole lot of application stuff. Not that we actually building stuff, but I mean, just understanding how things really work because you have to go into detail with a lot of stuff. That's pretty cool. So we have negative. So now remember, we're doing this thing right here. We're so let me make sure that the connection is made. I'm gonna make one more step. So I'm gonna have mv minus lambda v coming from this line. So this is line 1, this is line 2, this is line 3. And I just subtracted it to the other side. So now we have 0. So now we have m minus lambda v equals 0. So now we have what we called I minus lambda omega equals 0. And now we have what we're working on right now, which is line 6 of this progression. So hopefully that discussion I made about the eigenvalues, eigenvectors now connects you to what we're doing now. So now what we're going to do is I'm going to multiply this, and we're going to have negative 3 minus lambda omega 1 equals 0. We have 3 minus lambda omega 2 equals 0. And we're going to have, so all I'm doing is just doing matrix multiplication, multiplying this out. And we have 4 minus lambda omega 3 equals 0. So that means that negative 3 omega 1 minus lambda omega 1 equals 0. So negative 3 omega 1 equals lambda omega 1. So let's see what we can do here. I think that's good enough. We want to simplify this in a bit even farther, but I'm just getting what we need out of here. So we're going to say 3, just multiplying this out, 3 omega 2 minus lambda omega 2 equals 0. 3 omega 2 equals negative lambda omega 2. And this is 3. So then we have 4 omega 3 minus lambda omega 3 equals 0. So 4 omega 3 equals lambda omega 3. We have our lambdas up here. So all I did was just multiply that out. And now we're going to actually plug these lambdas in and see what happens. So we have lambda equals negative 1, lambda equals 3, and lambda equals 4. So for lambda equals negative 3, we have negative 3 omega 1 equals negative 3 omega 1. You see that? Mom says my brain light is excited about science. That's awesome. Science is nice. So what I can do is I could cancel this out. Omega 1 equals omega 1. This makes sense. So that means that's a free variable. We can say 3 omega 2 equals 3 omega 2. Okay, so that's another free variable. And we have 4 omega 3 equals negative 3 omega 3. That doesn't equal. So what does this do here? Forget what you do when it doesn't equal. Either it's not a free variable. I forget. That probably just means that there's another issue with the numbers, I guess. I just picked a random, what's it called, that works. But let's just say for the sake of argument that my numbers were slightly different. And let's say that this comes up to, let's say we had another term here. Let's just say that we had another term right here to make this, actually not right there. Which one is this, the W3 one? Let's say we had another term here to let you see how this would work if I had better numbers. And let's see how this would change. Let's see that number there. I'm going to try to look forward to try to make it work. Let's say that number is, there's 12. Say that number is 12. So that means that we would have, I'm going to multiply this out. And what I'll do is make these changes in green so it stands out. So now we would have 12 omega 2 plus that. So we would have, for this one, we would have 12 omega 2 plus 4 omega 3 equals lambda omega 3. So this then would be, and again, we're just saying that the matrix was slightly different. So that the numbers work. That is pick, random. When you pick random numbers, sometimes it doesn't work out. So when I plug in lambda here, this will be 12 omega 2 plus 4 omega 3 equals negative 3. So now we can do a little something. I'll write this a little bit better. Negative 3 omega 3. So what we can say now is, we can say that 12 omega 2 equals 7 omega 3. See how that works? So then we can say omega 2 equals 7 over 12 omega 3. And this is like, what happens when you have a problem like a professor might make, even though I'm sure they take time to make problems as well. Sort of kind of like making problems up on the fly. But if you had numbers that really work, it looks something like this. So omega 1 is a free variable. Omega 2 is a free variable. So I'm going to just say omega 1, I'm going to define that as 1, right? Omega 2 is a free variable. So I'm going to also define omega 2 as 1, which means that omega 3 equals 12 over 7 omega 2, which is 12 over 7. So that means that my eigenvector for this particular matrix, so I'll say omega negative 3, since lambda is negative 3, is going to be 1, 1, and 12 divided by 7, right? So that means that if, my numbers were chosen initially, that, all the numbers matched up, that means that that's the particular direction that this shape, I thought I drew it a second time. I guess I didn't. Oh, I did. Where did I draw it a second time? So I don't have to scroll this much. I need to highlight it better. Oh, well, maybe I erased it after I discussed it. But what that would mean is our initial shape that we had, our initial particle, all of these numbers were the same numbers. It will be able to rotate around the axes 1, 1, 12 over 7. So at 1, 1, a little bit more, it'll be able to rotate around that axis and not wobble. That'll be a primary axis. And the same process we would do for lambda equals 3 and lambda equals 4. So why don't we do that? So you can, let's do it for at least 3. So you can see what we're talking about. So I'll just write this over. We'll say lambda equals 3. So we're going to plug the lambda equals 3 in. And I'm going to go ahead and copy the equations that we multiplied from the original matrix times the vector. We can see what it looks like with a negative. And, well, it's not going to work again because the numbers are a bit off. Okay, that's all right. Why don't we just do the 4 one and see if that gives us a workable solution. So we'll do lambda equals 4 or negative 4. 4 or 4. This is regular 4. But the negative will probably give us the same issue. Maybe. Let's see. Let's see what it does. So lambda equals negative 4. That's positive. Okay. So we can say that negative 3 omega 1 plus 4 omega 1 equals 0. Yeah. I'm going to have to do the they're going to not equal. So these are some bad numbers, but y'all get the idea. So it's kind of is always odd making problems up on the fly because the numbers don't quite perfectly match with the dynamic. But you see the process. So the same process that we would do for 3, you would do for the other, whatever the lambdas are. And then you would end up with 3 eigenvalues. So let's say you're in eigenvectors. You'd have omega, whatever the other lambda is. You'd have an axes, let's see, to give you some examples from like the homework that we did where we had some good values of everything matched up. Like my next one might be 1, 1, negative 12 over 7, for instance. And then my last one, like there's always some kind of symmetry, because I mean, nature is symmetric. So things often work in a symmetric fashion. And you saw the matrix that we did earlier, we saw that it was symmetric, right? The eyes in yellow were different values, but they were on the prime axis. And the two in blue were the same, the two in green were the same, and the two in red were the same. So there's some symmetry because, if I'm pushing something on this side of the x-axis, it'll have the same effect as on the other side of the axis. Like nature doesn't care what we label things. So going back to the example that I did before, if I had the little volleyball attached to the string, if I start on this side and push it that way, everything is going to be the same as if I started on this side and pushed it this way. It's not going to make a difference. So that symmetry ends up being reflected in our answers where we have, similar values, but one is negative and one is positive. Or we might end up with similar values and let's say up here is plus minus 12 over 7, 1, 1. It's something like this. Or it might even be plus minus 12 over 7, 0, 0. And it'll probably just be one or the other. It'll be something like this. But they will have some kind of symmetry depending on the way the value is. And you will do the same process for this one vector. And you'll find all the prime axes where, for instance, a spinning top, I do a spinning top earlier, can spin and not wobble. All right, so that was a long problem. We're going for 3 hours. So I said problem marathon, but I guess it's still going to be a problem marathon. I'll be back. I'm going to take a short break, and I won't take a long break, like go get a snack or something. So y'all might need a break as well. What I'll do, I'll give a break. I'll take like 5 or 10 minutes, and I'll come back and do a Coriolis problem. I need to make my scrolling text bigger. I didn't realize I didn't put some good scrolling text. Maybe what I'll do is try to find a Coriolis problem online. Not as good with the Coriolis problems, but I got the right answer for the one for the homework. But I still dropped off something. So we'll be doing a lot of looking at the Coriolis stuff. Coriolis is basically, the Earth is spinning. So there's a certain amount of force, like if you're here on the planet. So let's say this is the Earth is rotating like so. And if you're standing here on the planet, it'll have a certain angular speed according to your spin, versus here where you're just spinning in space if you're at the pole. So what happens is if you're here and you have this certain velocity going in that direction, and a projectile is shot to the North Pole, by the time it gets here, it still has this side velocity here. So it's going to actually be, let's say, over here when it gets there. Even though I shot it straight up, because of the spin of the planet that it picked up here, is going to, by the time it gets to that latitude, is going to be high, is going to be to the side, even though it only had an initial vertical velocity. The same thing if we're on, I don't know, what? If you're building a space station and you know the space station is going to be rotating. So let's say you like on Deep Space Nine or something. See if I can draw Deep Space Nine really fast. It looks something like this, if I recall. There's like some spokes coming in. I believe it had like a something going out like this, right? And if you're walking out from the center of the space station out here, well, you're going to have some Coriolis force as well. You're going to have some centripetal acceleration, which is why you're not just flying out. You're going to have some centrifugal force coming out this way. And you're going to have some Coriolis force from the spin of the planet, in the space station. So all of these things need to balance out so that, you don't fly off the space station or something like that. It can only spin so fast. So, and common problems are like merry-go-round. So what I probably will do on my break, probably find a problem online somewhere so I can know I have some good numbers for it, because I'll feel less confident just doing it like I did here, where I just made up a problem because I knew what I was doing. So I was able to see when something wasn't sort of matching up how it should. While I'm on break getting a snack, I'll find a nice Coriolis problem. I'll link to the reference, and then we'll go through it, and I'll make sure I get the proper answer for it. So I'll see you all in, let's say, between 5 and 15 minutes. I'll just put my little links where you have the music going. I'll put a timer up, and when the timer's down, I'll be back. Hopefully y'all are back as well. I'll see y'all between 10 and 12 minutes. Thank y'all for joining. Let me go back to my screen. I think we have it. There we go. So let's see what we can do. What I have. So I've sort of been finding some things that relate, but not quite the same. So I may look a bit more, but I could just work through what I have, what I knew what I have at the moment. That's probably what I'll do. Welcome back, Mom. Good to see you. All right. So I can find a particularly good problem like I was looking for, but I have the idea. We'll work through some stuff. I'll put some reference links in the description, and we'll just work through this thing and try to understand it. All right. So, Coriolis. So a common example is the merry-go-round, and I did find a page that sort of gives the equations for it. You don't really explain it really. They give a good animation. So you might pull that up and look at that really fast. So check out that link I'll put into the description there, to the chat in the description. And we'll take a look at this. I'm not sure which window is showing on my, whatchamacallit now. The Comet NASA thing is still there. Whatever. Let's just try it out. Go around. All right. All right. That seems to be up. Let me get it situated again. Trim the top down some. Probably could trim the sides down some as well. So trim, let me increase the size a little bit. And I'll trim 100. All right. We'll go with that. And just leave it in the front for now. So this is the Purdue page, merry-go-round and the Coriolis component of acceleration. So welcome. And it says the video below shows 4 future ME274 students playing on a merry-go-round with the ball. It's quite interesting. The video is split between 2 views, one from a stationary observer looking down from above, and the other from a rotating observer on the merry-go-round. The stationary observer sees a straight path. The moving observer sees a curved path. Why is that, and what influences the shape of this path? So we can see very clearly. I want to see the straight one again. So we can see very clearly right there, the ball is moving straight from the perspective looking down. I think that's the coolest perspective, actually. So right there, the ball is moving straight when you're looking down from a fixed position that's not turning. It is fantastic. I mean, I just want to keep looking at it over and over. I mean, look at that. So looking down from the top, the ball is moving straight. You could clearly see it in a straight line. But on the merry-go-round, the ball is curving, which means they have to push the ball not to the person it goes to. Like right now, the person in yellow is pushing the ball to the person across from him. You see that? So the person in red is going to push the ball to the blue person. To do the Coriolis is going to go to the person in green. See right there, the red person is pushing it towards the blue person, but it's going to the green person. So they're pushing it straight, but the merry-go-round and the not just the Coriolis, because I mean it's going to be pretty small, but the angular acceleration and the Coriolis together makes that happen. It's pretty neat. Right. Analysis. Provided a solution video for this problem showing the influence of the Coriolis component of acceleration. Oh, they made a YouTube video for it. I mean, I could watch it up inside the window, I guess. Let me, if I need to adjust the volume, I guess it's not bad to comment on it. Why don't we go to this page first? Then I'll look at that and maybe we could just review that together. As shown in the analysis, a ball pushed. Oh crap! I'm gonna make this difficult. Okay, let me see if I can get this set up. I go back to just me again. On through the commercials. So we have this, have that. Let's see what this does. All right, well, it's something. Let's see. Let me know if this is too loud or something.
We're posed with the situation of a person that's standing over on the left side of this rotating merry-go-round is attempting to push this ball P directly toward B. In other words, an observer on the merry-go-round would see that the ball leaves this person's hand with a velocity vector, the relative velocity vector, pointing
draw this out
toward B. What we've seen from the video clips is that this ball will tend to actually curve to the left with the rotation of the merry-go-round being in a clockwise sense. And we want to use our moving reference frame equations to explain why that's true. So let's set up things. Let's write down, as we always should, to what our observer is attached. So we're going to attach our observer, in this case the person with the video.
It's actually pretty low, his volume.
We're going to attach this person to the merry-go-round.
Let's back up. I want to look at this illustration here. Make sure I get this down. We'll be doing that. The merry-go-round is in the XY plane. And notice how you can make your placement of everything convenient. So we have our Y vector going here right in the center. X vector here. So it's nice and symmetric. We have the merry-go-round is going clockwise. So this is our, I'll call it omega. It's spinning that way. In this case, it's constant. Find the acceleration of p as seen by observer on the merry-go-round. Okay, let's see what they do.
With the rotation of the merry-go-round being in a clockwise sense. And we want to use our moving reference frame equations to explain why that's true. So let's set up things. Let's write down, as we...
And this is P, by the way.
...to what our observer is attached. So we're going to attach our observer, in this case the person with the video camera in their hands. We're going to attach this person to the merry-go-round. In addition to that, as you can see,
it's still not like the problem I want to solve.
Video clip, and has the
but I'm sure it'll give some input, some insight.
Coriolis. We assume that the merry-go-round is smooth enough that again is a minus omega k. Minus omega k is a j. K cross j is a minus I. So the minus. A minus.
So thanks for letting me know, Rabbit.
Ends up being a minus r omega squared.
Hope the dinner going well, and glad you're still connected.
The j component is coming from k cross I. That's a plus j, and minus is all.
You're just using the same equations that we're using, which makes sense.
From the of the going to appear to, so right here, that's still with the vector. Which
right, so we're going to go ahead and do this thing.
Like this. Introducing the Old Spice NFL collection. Try again.
The relative velocity term.
So
minus omega cross.
I'm going to go ahead and draw what this person is doing. The link to this page is in the description in the chat. Let me close my window capture. All right. So we're going to attach the observer to the merry-go-round. And we'll just say that the observer is here. I'll draw a nice person standing on the merry-go-round. That must be a huge merry-go-round. Now, I know from class, we're going to be looking at these equations. So, force Coriolis is going to be -2 mv over r omega cross r. And F centrifugal is going to be -m omega cross omega cross r. We know those are vectors because that's a cross product. And F, what is this called? Angular acceleration, FAC, equals MAC, which equals V squared over R. So these are the three equations we can use to solve this problem. I think I'm going to solve it two ways. Oh, I've got my M. V squared over R for the M. Right? So these three forces are at play. All right? So looking at this, now one thing I want to understand is the direction of the forces. So let's say that we have, and I'm going to go back to the page. I think that page had a good drawing of this stuff. All right, so we're here. So looking at the merry-go-round here, at T, as shown in the analysis, a ball pushed directly towards the center of the merry-go-round will appear to have an acceleration to the left. That makes sense because is going clockwise, so this part of the merry-go-round is going to the right like this. So it's going to be carried to the right for an observer looking down. And this will produce a perceived curve path. So looking at it another way, if you're on the merry-go-round and the ball is going forward, it's sort of like the place it would have hit has already moved up to the right. Is that a good way to think about it? No, because that point is carrying the ball with it. I guess I'm thinking about the floor perspective. Let's draw this out. So right now he's talking about the stationary reserve perspective. Looking at it attached to the merry-go-round, the ball will come in and curve like we saw when we were moving around with the people on the merry-go-round. The ball will curve to the other person. Yet, let's take a look and see the direction of the path. If we're starting from here. So for the person looking down, the ball moves straight across. So the ball moves straight across, but the path for somebody on it looks like this. So this means that this point, so watch this here, this point that was here, by the time it hit the person, that sort of, so basically if this is T0, t equals 0, we'll call this point A. And let's say this is t equals t. Point A is here, right? So what happens is point A goes from there to there while it's rotating. The person on the merry-go-round sees the ball curve in space and just meet them after curving. The person looking at the ground sees the person move around and move in front of the ball so that the ball seems to go straight. Does light do this too? Technically, yes. It's just light is so fast that that we don't really notice it. But let's say, to exaggerate it, so we have the sun here, and we have the earth here. So we can say the earth is on a big giant merry-go-round, and we have light that's coming from a star here. But when we see the light, we've already moved here. So when the light was actually sent out from the star, we might have been here. Just like how the ball was shot when person A was here. But by the time the light hit us, we run around orbit here, and thus we see the star from this location. Just like how A went here and caught the ball there. Right? So the same thing happens. Oh, sorry. Hold up. I'm going to take this off. Let me draw that again. So if this is the sun, and we going around the sun in orbit, this Earth. If light comes from a star here, the light is of course going in all directions. But by the time the light reaches us, we've moved in our orbit to here. And thus we see the star from this location, but we had to move to that location. Just like how the person was actually here when the ball was first pushed, but they had to actually move here to catch the ball from the person looking down, or from the person sitting on the, merry-go-round. It looks like the ball curved to meet them there. But I guess you could say our perspective would be on Earth, ironically, because we're looking at the universe too. But suffice it to say that, now I guess the only difference is the ball is not rotating with us, the light is not rotating with us, but we do have to move into the location to receive that light. So that's where it's related at. It's not perfectly a match because the light is not spinning with us, but it definitely has a correlation. All right. Keep this party rocking. Okay, so we understand how that's going on. So again, I had these two pictures. Crap, I didn't mean to erase everything. I want to keep my two pictures. So I want to make sure I have this clear. So I've also simplified this picture. So I have one on each. We have, this is the attached and the observer from the outside looking down. So the attached person, the ball curves and hits the person at A. The person looking down, the ball goes straight and A moves to catch it. And the dotted one is what the person sees from the other perspective. The undotted one is what the observer in that perspective sees. The observer sees the ball go straight. The attached person sees the ball curve. But the person that's attached has to push the ball straight for it to curve to the person at A. And the observer sees the person just push the ball straight, and A is spinning at this angular frequency and moves in front of the ball and basically puts itself in front of the ball to catch it, just like I was saying with light going through the universe. So let's keep going. With this drawing. So now it puts the forces, the equations on the point T. I'll do the same thing. We have a vector there, a vector here, and a vector connecting these two. So these are basically the x and y components of these vectors. Right? So this is acceleration TO. Okay. So they're saying that this velocity, they're calling this O, this is the origin, the center, and the acceleration that the ball experiences in between P and O, the relative acceleration between those two is that. So the acceleration is actually going outside, which makes sense because whenever you have circular motion, like if you have, let's say, what's a good example? Like if you have a ball on a string and you're spinning it around, so it's going around in a circle, the acceleration is always going to be towards the axis of rotation. So the acceleration, the centripetal acceleration will be there, going directly inward to the center, which seems odd, but that's what makes it go in a circle. So since the ball is actually rotating like this from an observer on the outside, we see that this is the fulcrum. So the acceleration is going in this direction. And you can see that the vector A is parallel to that. So the thing about vectors is you can place them anywhere, as long as they have the same magnitude and the direction is the same vector no matter where you place it. And Mom says that makes sense. What about on a larger scale, as the spinning of the Milky Way? It's all the same thing, all works the exact same way. There's just at that point you're looking at light that's coming from another galaxy, which we see the Andromeda galaxy, which is I guess not a good example because we're moving towards the Andromeda galaxy. So as a galaxy, we're not necessarily, we might be orbiting it too, but I guess it actually starts to break down at a certain point because we've looked deep into space and we know that at a very large scale, galaxies make superstructures that looks like this, that looks like webs going through space. So one day I did a sort of talk about that and show some images of that. Maybe if I have time, I could find some of those images. But on a very, very large scale, it looks like that. And everything, I guess, is relatively stationary on that scale. But if you zoom in, you can have the Milky Way here, and we can have, not Andromeda, but whatever other galaxy there, and we could be moving relative to each other like that. Maybe there's like a big giant galaxy cluster here that we might be moving around. And the same thing, light will come from here and it'll have to meet us where we are, not where we were. It's like a football. But where we were, the light can't hit us because we're not there anymore. So it'll meet us where we are. Same process. It's pretty cool to think about. Everything is moving like that. Something that is unusual with light is like how this is the Milky Way and this is Andromeda and moving towards each other. So the light wave that would look like this if it was stationary looks like this because it's scrunched up because we're coming together. So all the frequencies of light is shifted up a little bit. So in other words, reds look a little bluer because we're going closer together. So that is one unusual thing with light that we see in space when things move toward or away from each other. That's how we can know they're moving towards or away from each other because the light is shifted. But that's a whole other topic. It is interesting. All right. So we have the angular acceleration. Oh, and one more comment I saw. Also, is the whole universe spinning whilst expanding? And what about around black holes? And do you think there's one in the center of the universe as well as in the Milky Way? Makes sense. Thank you so much. Don't know if the universe is spinning, but we couldn't know that because there's no reference point. Like the whole universe, all space is the universe. So yes, the universe can't spin because there's no space for it to spin inside. Seems odd. The space itself is expanding. What about around black holes? And do you think there's one in the center of the universe as well as the galaxy? Well, the thing about that is there's no real center of the universe. Like the whole universe is expanding. So technically we are the center of the universe. Like right where we're at. Like every single point is the center because that one point expanded. So I mean it does seem reasonable to think that it expanded from somewhere and there's a point that you can go to. Still haven't fully got to the bottom of that myself. But the idea is that there's really no center because everything is expanding away from everywhere else. And if there's a center, we wouldn't be able to see it anyway because we don't have a perspective, that big enough perspective. Everywhere you look in the universe, you look like you're at the center. If you look far enough out, everything is expanding from everything else at the same speed. Well, the relative same speed. We had to look at that in my cosmology class, in my galaxies class. And it's pretty cool stuff. You said you're welcome. All right. Now, this is one thing I was really interested in learning. Let's look at this thing. So they're saying that the centrifugal force, yeah, yeah, it will be this way because the thing is spinning around that way. So the centrifugal force is always outside from the center. All right. And I hate the fact that he's using a different form of the equation. I'll just stick with the one that the professor gave me. How can I make this the same form? I hate that. Awesome, Mom. I'm glad you appreciate it. Thanks for letting me know. Now, this thing, I hate that they gave me a different form, but I'm going to use it in the form that we have from class and try to see if I get the same answer. So F net, well, he's just doing acceleration. A net equals, so it's going to be A centrifugal plus A Coriolis. So that's going to equal negative M omega cross R plus, and this is going to be what? According to the coordinate system we have here, this will be negative I plus negative 2 mv over r omega cross r. And this is going to be in the positive j direction. Let me know if you have any questions about that. All right. Just look a little bit better. We have this. And all we have to do is figure these two things out. And this is in the j hat direction. And we can get the acceleration and then get the force. So one thing I'm really looking at is the direction of the forces. That's one thing I wasn't clear about, and I'm glad that we have this diagram. We know that the net force, so the motion of things is the net force. So Newton's law, F equals ma, is always a net force. Now, the interesting thing is, I need to look up this equation. I use this equation to solve a problem like this, but I need to remind myself which direction it's talking about. So I'll search v squared here. Centripetal force. Centripetal. So this is going to the inside. Interesting. So a centripetal. So what this means is that centripetal force would be, I mean, technically it should change, right? No, it should still be going all the way towards the center. It should still be going like this towards the center. Let's see. So in other words, if that particle was just stuck there, if it was not moving, if it was just stationary, right? And like it was stable to the merry-go-round, there would still be a force on it from the rotation if it's stationary. So the force centripetal will be pulling it inward. The force centrifugal will be kicking it outward. So there, right? So let's write that wrong because it's centrifugal. Yeah. So I wrote, well, it's both C, so that's making the confusion. So this is centripetal. I'll put CP. This is F centrifugal going outward. And then we have the Coriolis going up. Coriolis. I'll just call it CR. FCR. So hopefully these, right? So the Coriolis force is going up. The centrifugal force is going out. The centripetal force is going in, which means we can solve this problem with either so in other words, the centripetal force and the centrifugal force would have to be the same if it's staying stationary in that axis. And the Coriolis force would be related to the rotation of the merry-go-round. And Mum says, what happens if you send an object into dark matter, and is that really applicable in space flight as in pros considering all the light in the universe? But right now we're surrounded in dark matter. Dark matter is everywhere. It doesn't interact. So it doesn't hurt you. It's going through your body right now. So the whole Milky Way galaxy exists in a halo of dark matter. The halos of dark matter are where galaxies congregate. That's where enough mass is there to keep them together. So anywhere you see a galaxy, it's just totally infused with dark matter. It just goes through you and doesn't affect you at all. So it's not a big deal. But right now you're sitting in dark matter. Well, I mean, technically, we still don't know exactly how big they are, whatever. So imagine you passing through you randomly. You might not literally be sitting in a whole bunch of them, but generally through the day, I'm sure you get millions of dark matter particles. It's just all around us, and they balance their gravity out. How I see it. But on a gravity scale, it keeps the galaxy together. So if dark matter wasn't everywhere, the galaxy would have flew apart already. about how fast it's spinning. So we have to look at that in my stellar astronomy class. I believe we even calculated the rotation of the galaxy in the galaxy curve. And it's just spinning so fast that it wouldn't hold together unless there was more matter there than we see. That's one of the ways that we know dark matter is there. So, so yeah, it's everywhere. So don't worry about it. All right. So now we have the directions, and that we don't know. That is still a question that we're trying to figure out. They're trying to find out what dark matter is and isolate it. I bet you whoever does it's going to get a Nobel Prize, maybe like 5 or something. But that we don't know yet. We try to do a lot of experiments to find out. I wrote about that from my astrophysics course in undergraduate, and I looked at some of the experiments they're doing, different sensors that they're making and stuff like that, and so they're trying to find it. They're trying to identify it. There's some guesses what it might be, but we don't know yet. It's one of the biggest topics in science: dark matter and dark energy. Figuring out exactly what those are. When we find out, I'm sure you will know it. It'll be as big as relativity when that's found out. Probably even bigger than relativity. All right. So I don't think there's anything else I could do with this formula here. And technically, this is not a net. Thinking about it. Hold up. Plus a. Hold up. This is confusing. A centrifugal plus a centripetal. Called centripetal T. Yeah. I like dark matter and dark energy, which is why we were able to pick the topic we wanted to write about out of a list of topics. Like we couldn't just pick anything. And I picked dark matter for one paper and dark energy for the other. So I actually did a talk on this on MC Toon's channel. So if you know MC Toon, if you go to his channel and search in his history, you'll be able to find a talk that I did on dark matter and dark energy for about an hour. And I go into a little bit of detail, some detail. So just check it out. Let me know what you think about it next time you pop up. It's like about an hour long. A talk and a question and answer. Also did one on a conference this sort of conference company based in New York. I did a dark matter, dark energy talk. So that's pretty cool. I mean, I'm not an expert, but I did some reading on it and put some things together. All right, so here we go. I think we got this worked out. I think we got the placement of the things worked out. Let's look at this. One more example down here with this page here. These simulations allow us to compare and contrast a view of the path of the ball as seen by a stationary observer with the ball's path as seen by a person riding, which is what I tried to do here. I think I did it pretty accurately enough. So you can see how for the left one, you can see the ball curving, and you can see how it goes from A to Y curving. And the right one, hold up, I mixed them up. The left one is the curve. The left one is the one that's curving from A to Y. Like there's a curved path. It looks like a curved path in space. That's this curve here. That's the right one. So I did mine opposite. And the left one is the one where it's going straight. The ball looks like it's going straight. And you can see how point A, they call it point Y there. The point A or point Y moves in front of the ball and sort of captures it like a catcher's mitt. So at least I got that understanding accurate. Which is not a complicated understanding, I guess, but still, it's still new to me. We're doing Coriolis now. Mom says, wonderful, thank you, and you're amazing. Studying that to such a high level. I love your streams and we'll definitely find you on this channel. Awesome. Thanks for letting me know. Glad you enjoy. Now it's time to get some math. You all procrastinating on getting to this damn math. So let's forget this. All right. Oh, and I forgot to write one more thing. I got to write the the other force. So hold up. Yeah, because I'm gonna have to work this out. This one is new to me. Hold up. Did I mix up my forces? Centrifugal. Yep, right. Coriolis in the middle. And this is centripetal. All right. So we have plus v squared over r. And this direction will be to the positive x-axis. All right. So again, this thing, we're imagining that it's stationary. We're seeing that the centripetal force, pulling it inside, that's v squared over r. The centrifugal force wants to push it outside. That's the m omega cross r. And the Coriolis force is kicking it at a right angle to both of those. So that's one thing to keep in mind. The Coriolis force is a right angle to the centrifugal force and the centripetal force, the centrifugal and centripetal force, right? And it's in a direction towards the angle of spin. If you have a merry-go-round, it's spinning in the clockwise direction, which means that this side of it is going up. The Coriolis force is going in that direction. All right. Now, the thing is, since the centrifugal force and the centripetal force are equal and opposite, right? It seems we have to pick one or the other depending on the perspective that we're looking at. Oh, you know what it is? It's because the this ball happens to be rolling. So the only force, let me see here, the centripetal force, there's nothing holding it. That's why it's flying outward. So here the centripetal force will actually be 0. But since it's equal and opposite the centrifugal force, I could pick that one, which is why I got this problem right when I did this problem for the homework. I used the centripetal force because I'm more familiar with that one. And the Coriolis force was so small that it didn't play a part. So what that means is, really what I can do is, I'm going to have either this shall delete the right one. It's going to be either this, which is how I did it the first time, or this. That's playing a part in what happens. Right. So again, this one is the centripetal. This is the centrifugal, and this is the Coriolis. All right. So what we'll do is calculate both of these, and we'll actually see if we get the same answer. So we're going to just calculate these. So, and I'm going to calculate it at R. So R is just what it is. I'm just going to calculate it at that point and see what it experiences at that point. If that's a good idea. Maybe that's not a good idea, but I'm going to try it and see what happens. So we have A equals, now what I'm going to do is do some cross multiplication, simplification. And look, I need to remove M since it's an acceleration, not a force. All right. So we have negative omega cross. So this is going to be omega r sine theta. because of the definition of a cross product. And so this is going to be the magnitude of omega, the magnitude of r sine theta between omega and r. And we can see that omega is going around in a circle. So, I mean, at that particular point, now I'm exaggerating the arrow, but if I was to make that arrow very, very small, so it's like right, like very on the edge of that point, they're making a right angle to each other. So this is going to be 90 degrees. So this is going to end. I'm going to need to put a direction here. So let's call this direction. What is this direction? It's going to be up. So this is going to be in the z direction, if you see that. So this is omega cross r. Omega is going this way. R is going that way. Using the right-hand rule. So omega is going this way. R is going that way. So the cross vector is going upward. Right? And that's just using the right-hand rule. And it's going to be J plus. So now we have omega, the magnitude of omega. Magnitude of, negative magnitude of omega squared r sine squared theta. So now we still have omega going in the xy plane. The cross product of the xy plane, either x or y or x plus y, and j is going to be 90 degrees. So that's why it's going to end up being 1. And I'll just put theta equals 90 plus. So here we're going to have, well, let me just put the minus in. Minus, we have 2 mv over r. And then we have omega r and another sine theta. So now the thing is, this still has a negative I on the end. I think I'm going to have to deal with that negative I. And it still has a positive j. So maybe I don't have to deal with it because the right angle brought it up and then the other right angle brought it right back. So perhaps it's just going in the same direction. I remember my professor saying that when I went to speak with her. All right. So it says theta is 90 degrees. There's another theta sine of 90 there. So we have negative omega squared r minus 2 mv over r omega r. And let me check what my professor did, make sure I'm in the right path. Check M. Oh, but you actually put the force in there. Okay, so I wrote my equation wrong. Hold up. Yeah, I do have force up there. I just forgot. I forgot to delete the mass from here. So now it's acceleration and acceleration. All right, there we go. All right, so we have this. So that's acceleration. We'll call it A1 and A2 net. So A2 is that. So F2 equals negative m omega squared r minus 2m v over r omega r. All right. Now, let me see what's there's some difference here. V squared. Oh, okay. Let's see. All right. So this is going to cancel. Let me highlight these equations. I'm going to have to collect these equations later. right? So we have it equals, oh, I forgot, I have to keep my negative I. This is a vector, j. So these are two vectors, right? Negative I, j. All right, so if I was to plug this in at the origin, at r, well, that's just what it is. It's just, that's what it is right there. F2 equals negative m omega squared r minus 2 mv omega. Easy enough. And this is negative I and j. All right, easier than I thought. So now to get the force at that point, if I have some values, I can put it in to get the magnitude of the force, the magnitude of F2. That will be the square root of the two components squared. So this is going to be the square root of negative m omega squared r squared plus negative 2m v omega squared. So this is going to be the square root of m squared omega fourth r squared plus 4 m squared v squared omega squared. And that looks good. All right. So now we have the magnitude of the force at any given point on the merry-go-round as it spins around from the centripetal, what did I do? The Coriolis and the centripetal force. No, the central, yeah, centripetal, no, I did the centrifugal. Did I mix up my numbers? I think I mixed up my numbers. Yeah, I did. So hold up. This is 1. All right. Yeah, that's because I wrote them backwards. Normally I would write 1 first, but I want to actually do the one I wasn't familiar with first. Let me actually swap it up so that I don't do that again when I just look at it and think the first one is first. So I'll put it like that. All right, so we just did the first one, A1. Let's do the second one and see, well, the form is different, so I don't know if there's a way to say, oh, well, there is. Okay, let's look at this. So what this means is that the first term should be able to equal the second term. Let me show you what I mean. So F2, oh, I still got to change all my 2's to 1. F2 is going to be v squared over r I minus, and we already did this one, so we could just plug in the math that we did, which is 2mv omega j. This is negative I. So the right part is going to be the same. The correlate is going to be the same. The r is going to cancel 2mvw. That's going to be the same. Now, watch this on the left side. So if you have something going around anything, there's going to be the angular velocity. And oh crap. Oh, let me know if it's not showing. I just realized I was still showing the window thing. So the angular velocity is going around this thing. We have psi, and we can call this, you can say omega equals phi dot. The rate of the change in angle is the angular velocity. That's the angular velocity. And we can say that if this is r, we call this r. We can say that theta dot times r equals s dot if s is an arc here. So if s is an arc that's going across the that little part of the circle, that's going to be s dot. And so this is going to be omega r. And we'll see if we can get this into the same form. Oh, and this is going to be v dot. So not v dot, but v. So the change in the part here in blue is going to be the same, is going to match, that's going to match. So the distance that's traveled is going to be related to the angle and the radius that's traversed. So looking at this, we can say that F2 equals omega squared r squared over r. Oh, and I forgot my m. M negative I minus 2mv omega j. And of course, the r is going to cancel one of them on the top. So F2 equals the same thing that we had before. There's a negative here, negative m omega squared r negative I minus 2mv omega j. So you can see whether we do the centripetal force or the centrifugal force, since they're equal and opposite and they balance, they'll still give us a net force on the ball. You just have to remember that. Oh, and plus, this will be positive I. There we go. So now it's really equal and opposite. You can see that the magnitude of the F2 will be the same as F1. So everything is exactly the same. So F2 is the same thing. And there we have it. So we know we have to pick either the centripetal or centrifugal force and the Coriolis force to get the net force. Easy enough. So there's many things we can do with this. So we can find out what the force is at particular points on the merry-go-round, depending on the angular velocity of the merry-go-round. So let's say r equals 10 meters, and you want to, let's say, sit in the concentric center. So you want to sit at r equals 5 meters. And if you want the merry-go-round to go, what? What's a reasonable speed for a merry-go-round? I don't remember. Once every what? Once every 4 seconds? I think once every 4 seconds. So if the frequency is once every 4 seconds or 0.25 seconds, the period is 1 over f, which is 4 seconds. It takes 4 seconds to go around one time. I mean, that seems reasonable enough. Like we won't be killing any kids by flinging them off the merry-go-round at 100 miles an hour or something. And I'll have to remind myself what it is omega in terms of period. Let's think about this. So S equals by R, and we can say S over R equals 2 pi for one rotation. We can say that rotation think about this. I want to put period. I want to put omega in terms of the frequency. And I know it's a simple correlation, but I don't want to look it up. I want to figure out what it is. So omega is radians per second, if I recall correctly. So second in one period is 4 seconds. So omega t, radians per second times 4 seconds should also equal 2 pi. Because if it's going so many radians per second, and it goes enough radians to equal 1 full rotation, just one rotation, is going to equal 2 pi, which is going to equal S. No, it's not going to equal S. It's going to equal phi. Right? T is the period. Right? So omega equals T, phi divided by period. And that enough? Phi equals S over R. So omega equals S over RT. Now, take the period first. What does this come up to? It comes up to 1 over second, radians per second. If we could figure this out, if we calculate this correctly. So the radius is R, is 5 meters. 5 meters. We know S is phi R, which equals for one period. T okay, so 2 pi every 1/4 of a second. 2 pi every 4 seconds. Oh, it's easier than I thought. Hold up. T equals 1 over F equals 4 seconds. So it goes 2 pi per 4 seconds, or pi per 2 seconds, or pi over 2 per second, albeit the omega is pi over 2 every second. That's how fast it's going. Yeah, think pretty sure I would have got there. It is roundabout where I was going. Let me see what I would have ended up doing. I'm not sure. Let's back this up. Perhaps thinking about all those details helped me get to where I needed to get to anyway. So, simply put, the frequency is omega is radians per second. The frequency, at least the period, is going to be 4 seconds divided by 2 pi. That's how many radians. And it is called that omega, radians per seconds. And then just extracting those things out is going to be 2 pi over 4 per second, or pi over 2 per second. If we think about it, a circle is 4 pi over 2s together. So it's going 1 second power over 2, 2 seconds power over 2, 3 seconds power over 2, 4 seconds power over 2, which is the period. 4 seconds to go around the whole thing. In frequency, every let's see, it's not making sense to me though. Oh, rabbit, just about to get some garlic, so I popped in to say this is great, Daryl. Awesome. Thanks for letting me know. I appreciate it. Glad some entertaining and informational. Hopefully it's helping. So looking at this, why does the frequency not make sense to me? I understand the period is 4 seconds. It takes 4 seconds to go the way around one time. Frequency should be 1 over t, so t should be 1 over f. So 1/4 of a second I think I reversed these is what I did. Time around 4 seconds. Yeah, that's what I did. As a fraction. Third is 4 seconds. 4 seconds to go around one time. What does it mean that the frequency is 1/4 of a second? Unless I'm just thinking about that incorrectly. Let me look this up. Yep, frequency is 1 over t. So, and this is the length. I just have to look at one thing, the number of overall cycles in a certain period of time. So what it's saying is, in 1 second, 1/4 of the cycles are completed. I'll put the link in the chat and in the description. All right. That's not to make sense. So it takes 4 seconds to go around one time, which means that every 1 second, 1/4 of it goes around. So this is 1 second. Only 1/4 of it has moved past this point. And in 2 seconds, half of it has moved past that point. In 3 seconds, 3/4 have moved around that point. And in 4 seconds, the whole thing has moved around that point. So every second, 1/4 of it is moved around. I was thinking about it the opposite way before. I was like, how can it was taking 4 seconds to go around one time. How can it, at the same time, in a fourth of a second, go around one time? I guess I was thinking about it in the reverse way. So it takes 4 seconds to go around one time, which means every second, 1/4 of it goes by. 1/4 of it goes by every second. That's the frequency. And since it goes 2 pi in 4 seconds, radians per second, that's how far it's going in a second. So the angular frequency is pi over 2 per second, and we can see how that matches as well, because we'll put this circle back. 1 second goes by, again, pi over 2 goes by this point here. Another 1/4 of a second go by, pi over 2 goes past this point P. So that's how fast the angles are changing. Pi over 2 angles are going by every second. So it all adds up. So now we know that omega is pi over 2. And now we can actually figure this out. And we know that these things are equal. Each of the equations are equal. So it doesn't matter which one we use, because they're the same equation. So the magnitude of the force at r equals 5 is going to be the square root of, and I need to give myself a bit more room. Right? So the magnitude of at r equals 5, and I didn't give it a mass. Right. Let's just do 20 kilograms. So we have something on there that's 20 kilograms, right? So we have 20 kilograms where the angular frequency is pi over 2 per second. So pi over 2 per second to the 4th times 5 meters squared, because it's sitting right in the middle concentrically of the 10 meter radius merry-go-round, plus 4 times 5 kilograms squared. And then we have, I calculated velocity somewhere, or I can calculate velocity. I don't think I specifically calculated it yet. I think I just put the equation here somewhere. What did I calculate? V. Yeah, it's right there. V is omega times R. Okay. I think I shall calculate that separately, then plug that in. So V is omega R, because again, the arc length S is going to be the angle times R. So the arc length S dot, how much it changes, is going to be based upon how much the angle changes. So S dot is psi dot times R, as I wrote here, or S dot is omega times R, and S dot is V, how much the position changes, all right? So I could just multiply omega times R, which is going to be pi over 2, 1 over a second, times 5 meters, since we're 5 meters in. So it's going to be 5 pi over 2 meters per second. That's how fast this thing is moving around. So, tangentially, how fast it's moving around, all right? So we have 5 pi over 2 meters per second squared. Then we have omega squared, which is pi over 2 1 over second squared. All right. So I'm going to plug this into the hefty calculator, and we'll see. And let me make sure the units are working. We need force. Actually, I'll check that momentarily. Plug it in first. And I'm going to plug these in separately because I actually want to know what the Coriolis force, what the magnitude is in this scenario, so I can get a feel for it. I can start getting some intuition about this. We have 20 squared times pi over 2 to the fourth times 5 squared. Oh, it is squared. Everything is squared. So this is 6880 point, well, I'll just make it 881. And this is kilogram squared over a second to the fourth meter squared. So newtons is kilograms meters per second squared. So this is Newton squared, right? And Rabbit says, hey, I'm having a quick break before I mix up my burger meat. Still been watching and listening. Awesome, man. Thanks for letting me know. So I'll take a quick break in a bit as well because I was drinking something while I was working this last hour. So I need to run to the restaurant for a bit. But I shall be back. All right. So we have that plus, and now we have 4 times 5 squared times, now what did I do there? Well, that was, yes, all right. That was a tangential velocity. So that's 5 pi over 2 squared. And pi over 2 squared. So let's see what this is. Man, not a big number. We have 19,000. I'll just say 25. And here we have kilogram squared. We have meter squared over seconds to the fourth. You see that? So we have kilogram squared, meter squared over second squared. But then we have another over second squared. So that's still meter squared over seconds to the fourth. So newtons are kilograms meters per second squared. So newtons squared are in fact kilograms squared meters squared over seconds to the fourth. So that's a way that you can check to make sure that your equation is giving you valid amounts by checking the units. And if the units don't work out, then maybe I calculated my velocity wrong or something. All right. So this is going to be, so now hold up. So let's take a look at this. Now we know that the Coriolis force, that seems huge for a Coriolis force, really, but it is a big mass. So, I mean, I guess that makes sense. Oh, and plus, usually when I think about Coriolis, I think about the planet by default, but this is a merry-go-round that's going, once every 4 seconds is going around. We're at 5 meters out. So this thing is going around a circle of radius 5 meters every 4 seconds. So it's going, I mean, it's fast enough. It's 20 kilograms. Yeah. So that makes sense. And so the Coriolis force, the force is going to be, going back to the diagram, the force is going to be pushing in this direction that I'm going to highlight in blue. That is going to be 19,000. Well, the square of it is 19,000. And the square of both the centrifugal and centripetal force, if it's not moving, if it's static, but right now it's not static, so it's moving out. So technically it's only going to be the centrifugal force because it's moving outward, but it's going to, if it was stable, it would match the centripetal force. Yeah. So that's going to be square 19,000. So those are some big forces. But I'm going to have to add them together before I take the square root. So let's do that. But at least we know the square. Actually, let me take the square root of each of them. This is not going to give the answer, but I just want to see what the forces look like. So what this saying is that, oh, sorry, wrong thing a second time. To get some intuition about this, the centrifugal and centripetal forces are 246 newtons or 247 newtons, and the Coriolis force is 137 newtons. That's a lot of newtons for a mass just from Coriolis. The equation looks right, so it is what it is. Let me check the my notes from a professor one more time. The equation is right. I picked the big mass, what is 20 kilograms in pounds. £44. It's still, relatively light. Let's see how many newtons an apple is in weight. So an apple is 1 newton. Okay. About a quarter of a pound, just about. The apple is about a quarter of a pound. We're looking at 44 pounds. It takes 1 newton to hold an apple up. So this would be 100 apples worth of force. So like a big sack of apples, that's how much force is being put on you. Thinking back to a merry-go-round, did I have to hold on to the merry-go-round when I was spinning? I would say so. That seems reasonable. And Rabbit says meter squared over second squared is blowing my little brain, considering the acceleration in meters per second. Oh, you're talking about the meters per second foot right here? Yes, because it's squared. So what's going to happen is I'm going to add them together. So it's going to be the 19,001 plus the 60,001. That's going to give me just about 80 equals square root of, I'll just write it out, 79,905 newtons squared. And the square root of that is going to be 282 newtons. And ain't that something? So look at this. The magnitude is still very close to just the centripetal force. Do you see that? Even with a large mass, this is the centripetal force here. This is the Coriolis force. But you don't feel each separate, you feel the nets. So when I get the magnitude of these put together, it's still not much more than the centripetal force, which is why it takes, usually we don't have to calculate the centripetal force. That's amazing. I think that's amazing. I think that's awesome. I told my professor I was going to work a problem with more girth so I could see it more clearly. Now, so the meters per second squared thing, newtons is kilograms meters per second squared. And earlier we squared each of them to get the magnitude. So basically you can say that R is the square root of x squared plus y squared. So we have one of the forces going in the x direction and the other one going in the y direction. So we have to get the magnitude in that way. The magnitude of R. So now I have to square, so it's kilograms squared, meters squared over seconds to the fourth, plus kilograms squared, meters squared over seconds to the fourth. I added those together, so then I end up with just 1 kilogram squared meters squared over seconds to the fourth, which is just Newton squared. And then when I take the square root of Newton squared, I just get Newton. So that's what that was like. So yes, the Newtons do the units work. Newtons and Newton squared. So remember, it's meters squared over seconds to the fourth, and not meters squared over seconds squared. Meters squared over seconds to the fourth, or meters over seconds squared. And that's another way to look at that. So we looked at F equals ma earlier. This is Newtons equals kilograms, and acceleration is meters over seconds squared. And we look at velocity is meters per second. And if I was to take the derivative of velocity, it'll be dv over dt, which is going to be meters per second per second. And probably a better way to write that, meters per second per second. So we look at that, this is going to be meters per second divided by seconds. So this is going to be meters per second divided by second over 1. And we know if we divide something by a fraction, it's the same thing as flipping the fraction over. And that's how we get meters per second squared. So it's literally meters divided by seconds divided by seconds. So it's like a triple division that ends up just being seconds squared. There we go. So hopefully that helps. So I'll take a quick break. I need to go have a quick restroom break because I was drinking something earlier. But I will come back and I'm going to finish up some Coriolis stuff. Because we looked at how we can calculate the force, but we're gonna relate the Coriolis and centripetal forces with the normal force, and we'll see how that comes up a little bit. All right, so I'll put the break screen on again. I'll take 10 minutes. So come back in 10 minutes. I'll do some Coriolis, finishing it up, and then I'll wrap up. And I'll probably still be back later tonight to do some more of these, to do harder ones. So this is like the entree. I'm going to do a much harder inertia problem, like a 3D problem. And maybe I'll even do like a Coriolis with like a bullet or something. Or maybe a faster moving thing like a helicopter propeller. What if you put something on the helicopter propeller? We'll do something. But before all that, I'll just take like a 10-minute break and I'll come back and we'll do some normal force and see how that relates to the Coriolis. We'll be back in a bit. right, you all back. While I was breaking, came back. I actually found a pretty interesting video I'll share. I'll put it in the chat and in the uh, references. It's a pretty cool video showing how at the equator the uh, they make this device that's a little bit in the northern hemisphere, a little bit on the southern hemisphere, and right on the equator. And you can see how in the northern hemisphere the Coriolis force goes one direction, makes it spin in one direction. The Coriolis force makes it spin in the other direction in the southern hemisphere, and then on the equator the water just goes straight down. So we can see how the water drains down our drains is because of the Coriolis force. So it's pretty interesting. So it's very slight, but if you have something that's freely moving, you know, Newton's force, Newton's laws, net force. So if you have something that's not being impacted at all, it'll just go in the same direction it's going in. But whenever you put a force on it in out of direction, it'll cause some acceleration. There is some force, so there is some acceleration, and that's pretty cool. All right. I was going to mention some what do you call it? Normal force with this. So why don't we consider? So we have this 20 kilogram mass. Let's say that the merry-go-round it is on. So again, to review, we have a merry-go-round. The merry-go-round is spinning once every 4 seconds. The merry-go-round has a radius of 10 meters. It has a frequency of 1/4 second. So every second, 1/4 of it goes by. It has an angular acceleration of, what was it, 1/4 pi, 1/2 pi? Yeah, pi over 2 per second. Pi over 2 radians per second. What else did we find out about it? It has a tangential velocity at the edge. Oh crap! I just realized I did I put the wrong value in for my velocity? Hold up. Oh no, I put in 5 meters. I was good. I was just thinking maybe I forgot to change this to 5 because I forgot that it was not on the edge in this problem. But I did put 5, so I did catch it, so we're good. So at the edge, so I actually didn't calculate the angular velocity in the middle. I just calculated it. I mean, at the edge, just in the middle. But I would just actually put what it is. I would just say the angular velocity is WR, which is pi over 2 R per second. Okay. So I put in 5 at 5 meters like we did earlier is 5 half pi meters per second. If I put in 10, it's 10 pi meters per second. Yeah, that is cool, Rabbit. So I mean that is one, it's a clear indication of that we're on the globe. There's a clear indication of the different forces that are impacting us at any given time. Because you have little bitty water molecules that's moving around like that. Maybe I should, well, I mean, it's not too bad to show that video, I don't think. While we're discussing it, let me see here. Let me add that to my window capture. Yeah. Sufficient. Boom. And I shall go ahead and like and subscribe. That's a cool video. So there is in the northern hemisphere. You can see it's rotating clockwise from the top. So just so little bit above the equator. Southern hemisphere. You can see it spinning counterclockwise. Doesn't say floating for long, but you saw it going counterclockwise. And then right on the equator, 0 latitude, you can see it's just the water just going down. You're just going down into the hole. So Coriolis at work. And of course, the same thing happens to our storms. When I was looking through the videos, I saw a little clip of what do you call it? Neil deGrasse Tyson saying that how you know, hurricanes and stuff like that is affected. Pretty cool. So we have V equals that. And what other? I think that's all we really need as far as our established values. We do know that the magnitude of the force due to Coriolis and centripetal force, or at least centrifugal force, it is going outward. So centrifugal is the force that's acting. We know that F net is going to be 282 newtons. Okay. So what do we want to find out? How far do we need to put this? Oh, I need to put how much the mass was. The mass is going to be, did I say 20 kilograms? I believe I said 20 kilograms. Or is it 20 kilograms? Oh, no, that's the one I just wrote. I want to make sure, yeah, initially I put 20 kilograms. I don't remember where I wrote it initially. Maybe I just said it's going to be 20 kilograms. I thought I wrote it. Usually I write my units down. Well, I guess I didn't. I guess I just said it. As you can see, we put in 20 kilograms in the equation right there. And we know the mass is 20 kilograms. 20 kilograms for, I do have a 5 there. I just noticed I have a 5 right there. Or, crap, I did. Put in, I made a mistake and made that meters. But, this would have been a bit bigger. So this would be 20. Oh, well, let me see what the difference is with that 20. I put in the 5 for the, must have been thinking about what's we call them? The, meters and everything. And I got 5 happy. Let me just put 20 in for that 5. Oh, that's 30,000. It's still smaller, but it's a whole lot more. Let's get the accurate amount here. We have 30. Hold up. Oh, that's really big. Let me make sure I didn't miss something else. Hold up. 4. What it is. Oh, crap. I put in a 5 for the first one as well. Did I do that? Oh, put in a 20 there. All right. This is saying the Coriolis force is actually bigger than it was McClellan force. So here I made an error somewhere. Let's see. I just noticed I had a typo on my mass when I was remembering what the mass was. 304,403. So that'd be the square root of that plus this. So it's actually 604 newtons, which is a lot more. Oh, do that. Equation is right. See, the equation is right. It just is what it is. So maybe I'm thinking, maybe I'm spinning that, maybe I'm spinning this merry-go-round faster than I think. It's been a long time since I've been on a merry-go-round. Y'all let me know, is 4 times, is once every 4 seconds fast on the merry-go-round? And maybe the merry-go-round is huge as well. So 5 meters is what? 15 feet? Yeah, I don't think I've ever seen a merry-go-round 15 feet wide. Well, 15 feet across. So that'd be 30 feet, a 30-foot diameter circle. Yeah, that's a huge merry-go-round. All right, so that makes sense. But such a huge merry-go-round that is causing a very big Coriolis force because the radius is so far out. Right? Well, that's what you get when you make up problems on the spot. Sometimes the numbers are huge. I think in real life, like the problem that we had, one of the problems we were given, the angular acceleration was 3 radians per second. So let's see what this is when I actually calculate it out. So you have 2 over 4. It's not too bad. 1.57 radians per second. But that merry-go-round was, we were on the order of centimeters. Yeah. So the problem that we did, it was in the range of centimeters with the rotation. So yeah, that would explain it. You go from centimeters to uh, 10 meters. There'll be a drastic change. So I wonder how big a merry-go-round is. I could look that up really fast. How big is an actual merry-go-round? Size of merry-go-round. 6 to 10 feet. I don't even feel like doing the calculation, but it's like what, 2, 3 meters? 68 feet, like 2 or 3 meters. Yeah, 2 to 3 meters. Okay. So what I did was, well, they said it could be up to over 15 meters, right? Frequently, it's 2 to 3 meters. One says 4.5 to 15 meters. All right, well, big merry-go-round. Let's keep it rocking. Let's see what we get. Maybe mine 10 meters. So we're on the big end, but it's not unreasonable. Let's see what the speed, how fast do merry-go-rounds go generally. Well, flinging kids off to infinity, 3 to 5 miles per hour. Oh my gosh. In meters per second. 1 to 5 meters per second. What was my velocity? They go generally 1 to 5 meters per second. Mine is going at 5 meters. 5 times I over 2. Oh, okay then. So mine is going about 8 meters per second, tangentially. All right. So it is faster than the average merry-go-round on the upper end of the size of the merry-go-round. So it seems like the parameters is going to have a bigger Coriolis force, which stands to reason. So that suggests to me that Coriolis increases exponentially faster than centrifugal. let's look at this. We have meters squared. That's just going to give the force. We have omega to the fourth, whereas only omega squared over here. And we have position squared here and velocity squared over there. So let's see which is bigger. Well, I guess, it's like comparing apples to oranges, really. So they're different units, but it must be more impactful to square the angular acceleration. Well, okay. So if the angular acceleration stays constant, will you increase the radius of the thing? Then the centripetal force will increase only by radius squared, but the Coriolis force, I'm looking at the right side. Yeah, Coriolis force will increase by velocity squared. So really, it's a matter of, perhaps it's more a matter of the radius versus the velocity. And the velocity is going to increase by meters per second, which will be affected by the angular velocity. That's a complicated thing to look at. People have to graph it and see how the centripetal force increases relative to the Coriolis force at an increase in velocity versus an increase in radius. There might be a point at which below this speed of rotation, the centripetal force dominates, and above the speed of rotation, Coriolis dominates, or below this radius, one of the other dominates. And as you adjust the parameters, it changes which one dominates. My intuition tells me that it'll be like that. At a certain radius and a certain speed, one or the other will dominate more. And depending on what you change, it'll affect that. Look, let's keep on going. So what we want to know is, at what point on this merry-go-round can we put the mass of 20 kilograms if it has a coefficient of static friction of 0.3? And Rabbit says, that's interesting. Put my feet up for 5 and came into a fascinating point. Awesome. Glad you enjoyed. Physics is quite interesting. And 0.3 is a pretty standard friction. So what we want to know is, at what point can we put this mass so that it doesn't slip? If I put it too far out, the forces will be too strong and it'll slip. If I put it close to the center, well, it's not going to slip because it's not, it's spinning in place. But I guess I should say, what's the farthest out from the origin can I put this mass so that it does not slip due to the net force on it from its rotation, the centripetal plus the Coriolis force? What point is that, given this angle of acceleration, given all of this stuff that we have? Okay, so let's figure that out. So first thing we need to do is get the normal force of this thing. Normal force in is going to be the coefficient of friction times the force of gravity, which is going to be mu times mg, which is going to be 0.3 times 20 kilograms times, I'm going to just give myself some more room, times 9.8 meters per second squared at the surface. All right. So the normal force is going to be 0.3 times 20 times 9.8. All right. So the normal force is only 58.8 newtons. All right. And we can see again the kilograms meters per second squared. That's the newtons. So what that means is that at 5 meters, F net at 5 meters, given this angular rotation, which is faster than the average merry-go-round, is going to be that newtons. We need it to equal that newtons. So what's the best way to do this? Let's see. You want the radius. So what I would do is I would take how the equation would work. I shall do the more complicated one since that's the one I'm least familiar with. We have, this is the net force. And here we have the centripetal, and here we have the Coriolis. We know that this has to be less than or equal to 58.8 newtons. So what we can do is, I'm going to just call this, no, maybe N is bad. Well, I'll just keep it F net. It's not a big deal. All right, so we're going to say F net squared equals M squared plus M squared omega to the fourth R squared plus 4M squared V squared omega squared. Let me check my equation one more time, make sure everything is looking good. Squared omega to the 4R squared, 4 squared V squared. Yep. So we want R. So we have F net squared minus 4M squared V squared omega squared equals M squared omega squared, omega to the fourth R squared. So we have R squared equals F net squared minus 4M squared V squared omega squared, all divided by M squared omega to the fourth. We have the radius is going to be the square root of F net minus 4 mv omega squared divided by m omega squared all squared. You can see what I did there. So F net 4 mvw squared. All right. So all we have to do is plug this in to get what the radius will be, that the mass must be less than or equal to not fly off, to not flip. So we have the square root of 604 newtons minus 20 kilograms times the V we had was, oh crap, there's another R there. I forgot about that other R and V. Oh, I gotta go back. I gotta plug that in early. Hold on. Not necessarily. I don't have to go all the way to the end, I don't think. Let's see if I can plug this in right here. I need to put this V in terms of R. So R squared equals F squared. Make this squared look better. Minus 4M squared. And V squared is pi over 2R 1 over second squared. Omega squared. All divided by m squared omega squared. So we have r squared equals f squared minus, so I'm going to say 4 m squared the best way to do this notation. Pi squared over 4 r 1 over second squared omega squared divided by m omega squared. All right. Ain't that something? That makes it, I thought I was going to make it harder, but it actually simplifies it. We have r equals f squared minus 4 m squared pi squared over 4 1 over second squared omega squared divided by m omega squared. So let's look at the units here before I start plugging stuff in. So we have kilograms squared. Kilogram, well, it is kilograms squared. Then meters squared over seconds squared. So we've seen that before with Newton squared. M is mass. So this is 4, well, you could just use the numbers out. Kilograms squared. 1 over a second squared. 1 over a second squared. Kilograms squared. 1 over second squared. All right. That seems I mix something up in my math. Maybe I need to insert the do that insertion earlier. I think that's what got me. The v I might need to put that in earlier. What would it have done if I'd have put it in earlier? It was squared here, squared there. That didn't make a big difference. Oh my God! Did I use the wrong one? No, I didn't. R is meters. So, oh my gosh! No, I did square. What did I do? I did something here. I don't know what it is. Go back. So we know this equals newtons. We looked at that earlier. So there's something I'm doing here that causing it to break down. Oh, no. Second. Squared, meter squared over second squared, kilogram squared, meter squared over second, over second to the fourth. All right, I just did some algebra wrong. I don't know what I did. Let me just start this over again. The original formula is right, so I did something incorrectly there that's causing that to be wrong. So looking at this original equation again, we have kilogram squared 1 over second to the fourth meter squared, and we have kilogram squared meter squared over second squared 1 over second squared. That is kilogram squared meter squared over seconds to the fourth, kilogram squared meter squared over seconds to the fourth. So that's Newton squared. They add them together and take the square root is Newton. So we know that's right. I need to look at this more carefully and see what I did to make a mistake. We have f squared equals m squared omega squared r squared plus 4 m squared v squared omega squared. So this has to be meters per second squared. So we have m squared omega squared r squared plus 4 m squared. V is going to be pi over 2 r squared 1 over s. Actually, hold up. I think that's maybe what I did. I probably put a double squared. I was about to do it just now. But I think something in there, when I put it in parentheses and there was a square on the outside, I think I must have squared it in the inside and the outside. Similar to how those who were here earlier, I was putting a double negative on the, when we were doing the moment of inertia tensor, the equation, calculating each of the components, and I would put a negative on the outside and forget I put a negative on the outside and put it on the inside. So I need to watch that when I'm on the exam. I have a tendency to over negative things and over square things. So now that's meters per second squared and omega squared. So that equals, I'm going to simplify this right off the bat. This is going to be m squared omega squared r squared plus 4 pi squared over 4 r squared 1 over second squared omega squared. So now we have the 4's cancel. So now we have m squared omega squared r squared plus pi squared r squared omega squared. I would just say omega over seconds squared. Let's look at this. We have kilograms squared, meter squared over second squared. Oh, here we go over seconds to the 4th. So it happened again. What is happening there? Something is happening up in, oh my gosh. I'm having a typo on my 4th. Yep, right there, and I didn't write a 4 here. I copied this down incorrectly. Woo. Typos, man. But that's why I'm practicing. So I'll be aware of these typos. I'll take my exam next week. So I have to look out for double negative. I have to look out for the squares. Either a double square or I leave off a square. So I must have did one or both of these when I did it the first time. I left off a square and it wasn't working out, or a double square or something. And I have to watch out to not leave off the negatives. All right. So I think at this point, let's look at this. Kilogram squared, meter squared over seconds to the 4th. Yep. Kilogram squared, meter squared, and second. Right. Yeah. So this is 1 over second squared. Yeah. Now it looks right. All right. So let's continue to go through this carefully. So we have f squared over m squared equals omega squared r squared plus, we need to get the r separate. So actually, let me keep the r separate. You know what I can do? I can actually do that now as well. R squared, so it's going to be omega to the 4th plus pi squared omega over second. All right. So we have r squared equals f squared over m squared. And then we have 1 over omega to the 4th plus pi squared omega over seconds squared. All right, so let's look at this again. We have, I should have meter squared when I finish with this thing. So I have Newton squared here. That's mass, so that's kilogram squared. And then we have this 1/2 to the fourth plus 1/2 to the fourth. That's a sum. So that's going to be Newton squared over kilogram squared, 1/2 to the fourth. And as we saw earlier, if you have a fraction in the denominator, that's just seconds to the fourth. So newtons is kilogram squared, meter squared over seconds to the fourth when it's squared. Then seconds to the fourth over kilogram squared. And then we could cancel this stuff out. Kilogram squared cancel, seconds to the fourth canceled. And we're left with meter squared, which is what we need. Okay, so we're good. So now, let me look at Rabbit says, definitely be careful with your typos, Daryl. Men have such messy writing. Don't do that in an exam. Practice now. You are correct. What would you say, by the way? And don't worry about hurting my feelings. On a scale from 1 to 10, what is the readability of my writing? Is it it's not a 0. You can at least read a little bit of it, but it's definitely not a 10. So what would you say, Rabbit, and the other person that's watching? 1 to 10. So maybe I'll put that I'll make a little text to that. Let's say rate my writing. That source text. Yes. We're gonna put this where it's visible, but not too. Well, I do have room. I could actually move my pad over a little bit. 6.7. Okay, it's not horribly bad, but there's definitely some room for improvement. How to get better at that. Thanks for letting me know. I'll work on that. I'll see if I can get it to like a 7 for the rest of the demonstration. So I'll finish this problem, like I said, and then I'll call it. But I'll come back later. But I'll finish this problem. I'll go get something to eat, and I'll be back for my regular time at 8, which might be too late for some. You could check it later. But I'll give it what? I'm going to finish this in about 5 more minutes. Boom. So we have that. All right. So I'm going to try and increase this last part to a 7. Let's see if we can do it. Solve this last problem next 5 minutes. We have r equals the square root of all of this, f squared over the mass squared, 1 over omega to the fourth plus I squared and omega. What's the best way to omega squared and 1/2 to the fourth. 1/2 to the fourth, 1/2 to the fourth. Okay. And all I have to do is plug this in, and we're going to see what the radius is. Thank you, bro. I appreciate it. All right. So we have square root, and when I have to figure out, I know there's a way for me to connect my calculator to the computer. I'm going to figure that out so y'all can see what I type in. But, I'm just typing in what we have here. So we have 604 newtons. All right. We have 20 squared. What's the mass? I'm going to multiply that by 1 divided by, so omega to the fourth. So that's going to be pi divided by 2 to the fourth. So again, that's just this omega here. I'll highlight when I type them in. This is the force. Mass is kilograms. All right. So pi over 2, that means radians per second squared. 10 to the fourth. Then we have plus pi squared. Right. Then we're going to multiply that by omega squared again. So that's pi over 2 squared. Okay. I think that's all I have to plug in. Ain't that something? And you wouldn't you believe it. Look at this. It's 0.22 meters, which makes sense. That's a whole lot of force right there. That's a whole lot of force right there. At 5 meters, right? And we need that force to be 58 meters. Excuse me, newtons. So at 5 meters, it's 604 newtons. And we need the force to be 58.8 newtons. So you literally have to put that mass right there. I mean, right there. That's what? That's 150 meter, just about. So that's what? A meter is about 3 feet. I know. Meter is about 3 feet. 1/5 of that. So 3/5 a foot. Around what? 3/5 a foot. About a quarter of a foot. Foot is what? 12 inches. So about 3 to 4 inches. This is like a rough estimate. So you're talking about you need to put that thing about 3 or 4 inches from the center, or it's going to slip, given that amount of friction. Which is why when you're on the merry-go-round, you have to hold on, right? So that makes sense, right? You don't hold on, you start sliding out, right? I remember that when I was a kid, having to hold on. Right, y'all? Glad it is better. Yes, a little bit better. I think this is my favorite line right here. So I'll work on it. So when I do my classes, I plan on using the pad a lot. Right now, when I do my key for a mechanics lab, and only a few times I had to actually write equations for the class. Usually, and when it's complicated, I will use my pad. Like there was one day we had, I can't remember what that was. What was that? Oh, that was net force with. I remember what we did, but we had like a complicated vectors like in 3 dimensions, and you had so I wrote that out for them and on my pad so I can make it very, very clear. But if it's like one formula, I would usually write it on the board because we leave it on the board for the other labs. So it depends on how complicated it is. But awesome. Thanks, Rabbit, for watching. Thanks for commenting. Always good seeing you. Look forward to seeing you again. It's nice to have someone to work with, engage with, answer questions. And we have some other people here as well. Mom, thank you for coming as well. Good questions on cosmology, astrophysics, the universe. So maybe I can make a stream about that in the future. So I gave like some very brief answers to make sure not to go too much off the main topic, but want to make sure I address them as well. So hopefully that whet the appetite. And those who haven't, matter of fact, maybe I can find that really fast as I close up to make it easier for y'all. I had mentioned my talk on MC Tunes channel. I want to find that. I'm going to put that in the chat while the chat is still going. So pretty much all I have to do is search MC Tune, Daryl, Dark Matter. Should come up, and it did. So box is shared right now. Copy. So I'll put that in the live chat. I'll put that in the description as well, so y'all can check that out. See me give a little talk, undergraduate level. It's not super high tech. And I'll put that in the description as well. So I'll be back at my normal time, which is 4 hours from now, 3.5 hours from now, and I'll do some more complicated problems. So thank you all for showing, doing some science for y'all. I'll see those who are here in about 3 hours, 3 to 4 hours, 3.5 hours to be exact. You all have a good one.